Hello there, and welcome to Science for Sleep, where curiosity gets cozy, questions settle softly into the evening, and the universe becomes something gentle enough to explore with your eyes half closed. Tonight, we are turning our attention toward events so powerful, so energetic, and so astonishingly extreme that they can outshine galaxies, bend space itself, tear stars apart, and send waves across the cosmos that travel for billions of years before quietly brushing past Earth. Our subject is violence, though perhaps not in the human sense of anger or intent. The universe has no temper to lose and no grudge to hold. Its violence is mechanical, natural, and vast. It happens when gravity pulls too hard, when pressure builds too high, when magnetic fields twist beyond their limits, or when matter finds itself in the wrong place at the wrong unimaginable time. That may sound dramatic, but there is something oddly calming about it too. Because all of these colossal outbursts, collisions and cosmic catastrophes happen far away, often at distances so enormous that the mind can barely keep hold of the numbers. They unfold in silence. No roaring flames, no cracking thunder, no alarm bells ringing through the stars. Just light, motion, radiation, gravity, and time doing what they do best on scales that make our busiest days seem wonderfully small. Before we begin, I would love to know something simple. Where in the world are you listening from tonight? And what time is it in your little corner of Earth right now? Perhaps it is late evening, and the house has gone quiet. Maybe dawn is beginning somewhere outside your window. It could be the middle of the afternoon, and you're simply in need of a calm place to rest your thoughts for a while. Wherever you are, whatever hour the clock insists upon, I am glad you are here. And if you find this journey soothing, interesting, or just a pleasant companion for winding down, I would be ever so grateful if you liked the video, subscribed, or shared this sleepy little corner of science with someone else who might enjoy drifting off while learning about black holes, exploding stars, and the occasional deeply inconvenient burst of radiation. Now there, let us begin gently. When we hear the word violent, we usually imagine noise, urgency, sudden motion, broken things, raised voices, perhaps someone dramatically knocking over a chair for emphasis. The universe, however, tends to be more efficient. It can unleash energies beyond comprehension without making the slightest sound. In space, there is no air to carry a scream, no atmosphere to transmit the crash of impact, no nearby witness to say, "That seemed excessive." Instead, cosmic violence arrives as light. A star may spend millions or billions of years behaving responsibly, steadily turning hydrogen into helium, shining with admirable consistency, only to end its life in a blast so bright it can briefly rival an entire galaxy. Two dead stellar cores might orbit one another for ages, spiraling inward little by little until they merge in a final instant that sends ripples through space-time itself. A black hole may wait patiently at the centre of a galaxy, gathering matter with quiet determination, then suddenly release jets of energy across distances so large that our own solar system would look like a speck in comparison. These are not rare in the sense of one-time miracles. They happen across the universe constantly. Somewhere right now, as you listen, a star is collapsing. Somewhere else, two galaxies are sliding through one another in a slow-motion collision that will take hundreds of millions of years to complete. Somewhere farther still, radiation from a blast older than humanity is crossing dark intergalactic space, still on its way to some future telescope. It is strange, isn't it? The night sky can look peaceful. A few points of light, a dark background, a quiet ceiling above sleeping cities and oceans. Yet hidden behind that calm appearance is an arena of staggering forces. The stars do not merely glow, they fuse matter in their cores at extraordinary temperatures. Planets are not simply hanging there, they are falling endlessly around their suns. Galaxies are not frozen ornaments. They spin, merge, feed central black holes, and reshape themselves over time. Even emptiness is busy. If one could watch the universe sped up like a time-lapse film, the calm heavens would become a place of motion and upheaval. Stars would blink into existence and fade away. Gas clouds would collapse and ignite. Galaxies would stretch and collide. Streams of matter would arc into black holes. Invisible waves would pulse outward from mergers. It would look less like a still painting and more like weather. Grand, relentless, ancient weather. Perhaps that is one reason these topics feel so compelling. They remind us that stillness and activity can coexist. A quiet room may contain a racing mind. A calm face may hide a busy day. A peaceful sky may conceal stars detonating beyond imagination. And yet, for all this violence, the universe is not chaotic in the careless sense. It follows rules. Gravity gathers matter. Pressure rises. Energy transfers. Motion continues. Even destruction often builds something new. When a massive star explodes, it does not merely vanish. It scatters heavy elements into surrounding space, ingredients that may one day become new stars, rocky planets, oceans, metal tools, tea kettles, or listeners quietly trying to fall asleep while hearing about supernovae. That means some of the atoms in your body were forged in events we would classify tonight among the most violent ever found. Calcium in bones, iron in blood, oxygen you breathe, carbon that forms so much of life. These materials were made in stars and distributed by stellar death. The universe, while dramatic, is also generous. There is comfort in that thought. Catastrophe at one scale becomes possibility at another. Of course, human minds are not naturally built for cosmic numbers. If I say a blast released more energy in seconds than our sun will emit over billions of years, the sentence sounds impressive, but it is difficult to feel. If I say two black holes merged with masses dozens of times that of the sun, converting some of that mass directly into gravitational waves, it sounds important, yet still slippery. So during our journey together, we will move slowly. We will take these immense ideas and hold them one at a time. We will compare scales carefully. We will let the science stay accurate without letting it become stressful. No exam at the end, no urgent memorization required. Just a steady walk through the loudest things ever discovered in a universe that somehow presents them to us through silence. You may also notice something else as we go. The most violent events are not always the fastest. Some are sudden, yes, a flash lasting seconds, a collision completed in moments, but others unfold over ages. Galaxies can take hundreds of millions of years to merge. Black holes may spend eons drawing in matter before producing visible outbursts. Massive stars can live long, stable lives before ending explosively in a final brief act. That is very much the universe's style. It waits longer than we can imagine, then acts decisively. Human schedules are different. We become impatient if a web page loads slowly. We sigh at traffic lights. We refresh delivery tracking pages as if our attention powers the van. The cosmos is in no hurry. It can spend 500 million years setting up a collision and consider that perfectly reasonable planning. There is something healthy in remembering that. Your unfinished email, delayed plan, awkward conversation from Tuesday, and mysteriously unresolved laundry pile all exist inside a reality where stars take millions of years to prepare a finale. Perspective does not solve everything, but it can loosen the grip of urgency. Another surprising truth is that many cosmic disasters are beautiful. A supernova remnant expands into glowing filaments and shells of colour. Jets from black holes carve elegant beams across space. Colliding galaxies twist into luminous arcs. Nebulae formed from stellar wreckage become some of the most photographed objects in astronomy. We are used to separating beauty from violence, but nature often mixes them. A waterfall erodes stone. Lightning splits trees. Volcanoes destroy landscapes and enrich soil. In the universe, explosive death can paint structures of breathtaking grace. This should not be mistaken for romance. The forces involved are real and merciless. Stand near them, and there would be no poetic lesson, only swift consequences. But from a safe distance we are allowed another response: wonder. And wonder is useful before sleep. Not the sharp kind that keeps thoughts racing, but the soft kind that gently rearranges priorities. The kind that says there is more out there than the inbox, the errands, the tension in your shoulders, the conversation you wish had gone differently. Somewhere beyond the clouds and city lights, stars are collapsing into neutron stars so dense a spoonful would outweigh mountains. Somewhere black holes are circling one another faster and faster before merging into a single deeper darkness. Somewhere magnetic fields around exotic stars are snapping with enough force to disturb detectors across the galaxy. Meanwhile, here on Earth, perhaps your blanket is warm, the room is dim, and gravity is behaving in the modest civilized manner to which we have become accustomed. Not every corner of the universe can say the same. As we continue, we will ask a simple question. What truly counts as the most violent event? Is it total energy released? Brightness, speed, temperature, destructive potential, ability to distort space and time, duration, surprise factor? Scientists love metrics. The universe tends to ignore categories, so we will explore several contenders, each extreme in its own way. Some will involve stars dying, some will involve stars colliding, some will involve black holes doing what black holes do, which is usually either consuming matter, warping reality, or causing everyone nearby to regret their orbital decisions. Others will come from the early universe itself, when conditions were so hot and dense that ordinary language begins to fail and equations politely take over. And through it all, we will keep returning to the same gentle contradiction. The loudest things we know happen in silence. The fiercest events can create future worlds, and the night sky that looks still above us is anything but still. So if your breathing has slowed a little, if the day is beginning to loosen its grip, if your thoughts are ready to wander beyond streets and screens into colder, wider places, then we are in exactly the right mood. If we are going to talk about the most violent events ever found in the universe, we should first ask a deceptively simple question. What do we actually mean by violent? On Earth, the word usually comes wrapped in human context. We use it for storms that destroy homes, earthquakes that shake cities, wars that cause suffering, or sudden acts of force that harm living things. Violence in our daily language often includes pain, danger, fear, and intent. It carries emotion. It implies damage done to someone. Space, however, is not emotional. The universe does not become angry. A black hole does not hold grudges. A supernova does not wake up one morning and decide to make a scene. There is no cosmic committee voting to cause trouble near a spiral galaxy 3 billion light-years away. Instead, what we call violence in astronomy usually means something more mechanical. It means extreme releases of energy. It means rapid change under enormous forces. It means matter being accelerated, compressed, heated, torn apart, or rearranged on scales that feel absurd to creatures who still occasionally lose battles with jam jar lids. That distinction matters, because once we remove human emotion from the word, something interesting happens. Cosmic violence becomes less like rage and more like physics under pressure. A star collapses because gravity wins. Gas explodes because pressure builds. Matter spirals inward because momentum and attraction guide it there. Two dense objects collide because they have spent ages orbiting closer and closer, following equations with patient inevitability. There is no malice in any of it, only consequence. Now, if you were an astronomer trying to measure violence, you would quickly run into a problem. Which kind of extreme behaviour counts the most? Imagine 3 events. One is unbelievably bright. Another releases enormous energy, but over a long time. A third is not bright at all, yet bends space itself and sends out gravitational waves. Which one wins? This is where science becomes wonderfully fussy. We need categories. The first and most common measure is total energy released. Energy is the universal currency of dramatic events. If something pours out more energy than almost anything else, it gets our attention. This is why supernovae, gamma-ray bursts, and feeding black holes often top the list. Their energy output can exceed what our sun emits over millions or billions of years, compressed into far shorter spans. That is difficult to picture, so let us compare gently. The sun shines constantly. Every second, it converts millions of tons of mass into energy. It has done so for billions of years and plans to continue for billions more. It is steady, dependable, and frankly one of the more responsible stars in the neighbourhood. Yet some events elsewhere can briefly outshine not just one sun, but entire galaxies containing hundreds of billions of stars. That is the sort of thing astronomers notice. Another measure is power, which is energy released per unit time. This is slightly different. If I slowly pour a bucket of water into a pond over an hour, that is one thing. If I dump the same bucket in one instant, that is another. Same total amount, different intensity. The universe uses this distinction often. A quasar, for example, may release staggering energy for millions of years as matter falls into a supermassive black hole. A gamma-ray burst may release an astonishing amount in seconds. One is a furnace, the other is a flashbang. Both are extreme. They simply specialize differently. Then there is temperature. Some cosmic events heat matter to millions or billions of degrees. That matters because temperature reflects particle motion and energy conditions. Hotter environments often signal more violent interactions. Shock waves from exploding stars, accretion disks around black holes, and early universe conditions all score highly here. Still, heat alone does not tell the whole story. Your oven is hotter than your refrigerator, but neither is currently merging neutron stars. So we continue. Speed is another contender. How fast is matter moving? In many violent events, material is launched at thousands of kilometers per second, or even close to light speed. Jets from black holes and gamma-ray bursts can accelerate particles to astonishing velocities. Fast-moving matter carries immense kinetic energy, and when it collides with surrounding gas, things become even more interesting. There's also pressure and density. Some of the most extreme places in the universe are not flashy at all. Neutron stars, for instance, are remnants of dead massive stars crushed so densely that atomic structure itself is transformed. Their interiors contain matter under conditions impossible to recreate fully on Earth. Would you call that violent? Many scientists would say yes, though it is a quiet kind of violence, a relentless compression rather than an explosion. This introduces a useful truth. Violence in space can be sudden or slow. We humans are impressed by sudden events, loud bangs, quick impacts, instant transformations. But the cosmos often works on timelines that make patience look lazy. Galaxies collide over hundreds of millions of years. Their stars usually pass by one another because space is so empty, but gravity reshapes everything gradually. Gas clouds compress. New stars form. Central black holes may awaken. Entire structures are rearranged in a process slower than continental drift. And yet, in cumulative terms, it is one of the grandest upheavals imaginable. If you sped it up in a time-lapse, it would look spectacular. That is another lesson astronomy teaches repeatedly. Speed and significance are not the same thing. Now let us consider brightness. Because humans are visual creatures and telescopes often first detect light. Brightness can be misleading. Some violent events are easy to spot because they blaze across space. Others are hidden by dust. Some emit mostly X-rays, gamma rays, or radio waves rather than visible light. Some produce almost no light at all, and reveal themselves through gravitational waves or their effect on nearby matter. This means the universe can be doing something outrageous while looking quite calm. A black hole itself emits no light, yet the region around one, where matter heats and spirals inward, may become one of the brightest places in a galaxy. Likewise, two black holes merging can release enormous energy through gravitational waves while producing little visible spectacle. Imagine the most dramatic performance in town happening behind closed curtains, detectable only because the building itself vibrates. That is sometimes how astronomy works. Another important factor is scale of destruction. Could the event sterilize planets nearby, strip atmospheres, disrupt star systems, reshape a galaxy? Gamma-ray bursts are particularly famous here. If one occurred close enough and pointed toward Earth, it could damage the atmosphere significantly. Thankfully, space is large, timing is rare, and the universe has so far refrained from arranging such a discourteous appointment. Distance often protects us from cosmic violence. A supernova in another galaxy is beautiful data. A supernova too near Earth would be a more stressful experience. Fortunately, most of the universe's worst behaviour happens very far away. This allows us to admire safely, much like watching a thunderstorm from indoors with tea. There is also the question of rarity. Some events are violent but common. Stars flare, asteroids collide, magnetic storms happen. Others are so rare that we treasure each detection. The merger of two neutron stars observed through both light and gravitational waves was a landmark moment because it opened new ways of studying the cosmos. Rare events feel special, though common events can still be immense. Think of rainfall versus volcanoes. One happens frequently, one less so. Either can command respect depending on circumstance. The same applies in space. At this point, you may notice that ranking violence is less straightforward than it first seemed. That is because nature does not organise itself around our labels. We like lists. Top 10 strongest storms, largest animals, fastest aircraft, most violent cosmic events. The universe simply behaves, and we arrive later with clipboards. Still, labels help us learn. They give shape to curiosity. So throughout our journey, when we say violent, we're really using a shorthand for combinations of these features. Enormous energy, rapid release, extreme motion, immense pressure, transformative destruction, large-scale consequences, sometimes unusual rarity, and often all of the above at once. There is something humbling in this. Our everyday sense of force is tied to human scales. A crashing car feels powerful, a hurricane feels overwhelming, a volcanic eruption feels colossal, and they are, within the context of life on Earth. But astronomy expands context dramatically. A modest stellar flare can dwarf all human energy use. A routine supernova can outshine civilizations that do not yet exist. Black holes casually manipulate masses larger than our Sun while obeying gravity with unsettling confidence. Yet none of this makes our own experiences trivial. Scale is not a competition. A difficult day is still difficult even if quasars exist. A sleepless night remains real though galaxies collide elsewhere. Perspective should comfort, not dismiss. What cosmic scale can do, however, is soften certain anxieties. The email can wait a little. The awkward moment from last week is not visible from Andromeda. The universe contains neutron stars colliding at fractions of light speed. You are allowed to unclench your jaw. Another curious thing about violence in space is how often it creates, rather than merely destroys. A supernova tears apart a star, but spreads heavy elements needed for future planets and life. Galaxy collisions trigger star formation. Shockwaves compress gas clouds into new suns. Even black holes, dramatic as they are, can regulate galaxy growth through jets and feedback processes. So destruction and creation are frequently partners. That may be one reason these stories feel compelling rather than merely grim. They mirror a pattern seen in nature and life more broadly. Forest fires clear old growth and open niches. Storms reshape coastlines. Pressure forms crystals. Endings make room. The universe just does it with more radiation. As we move forward, we will meet several candidates for the title of most violent. Some explode, some merge, some feed endlessly, some distort time and space, some belong to the early universe when everything was hotter, denser, and less interested in moderation. We will compare them carefully without rushing, because the numbers are large and the mind deserves time to stretch around them. And perhaps the best working definition to carry with us is this: a violent cosmic event is one in which ordinary balance fails, stored energy is unleashed, and the surrounding universe must adapt. That could mean a star collapsing in seconds. It could mean two dead suns colliding after a billion-year spiral. It could mean a black hole eating too enthusiastically. It could mean a galaxy meeting another galaxy, and both pretending they meant to do that. Step outside on a clear night, and the universe can seem almost suspiciously peaceful. The air may be cool, street sounds soften into the distance, houses settle into their own quiet routines. Somewhere a dog decides that now, specifically now, is the ideal time to comment on something unseen. Above it all hangs the sky, dark and still, sprinkled with points of light that appear steady, patient, and ancient. It is one of the most calming sights available to us. No flashing warnings, no obvious motion, no signs of urgency. The stars seem fixed in place, as though someone carefully pinned them there long ago and then wisely decided not to touch anything further. Even planets glide so slowly that only careful observation reveals their wandering. The moon rises with practiced composure. Constellations return season after season like reliable old neighbours. And yet this peaceful impression is deeply misleading. The universe is not still. It is busy beyond easy comprehension. That quiet sky above you is filled with motion, tension, heat, collisions, radiation, collapse, expansion, and processes so energetic that our everyday language tends to become flustered trying to describe them. The calm appearance comes mostly from two things: distance and time. Those two are masters of disguise. Distance hides scale. Something unimaginably large can look tiny if it is far enough away. Time hides motion. Something moving quickly can appear frozen if its changes happen over spans much longer than a human life. Together they make the cosmos look serene. Consider the stars. Many of the lights overhead are not gentle lanterns hanging in darkness. They are giant spheres of plasma, heated to thousands or millions of degrees in different layers, powered by nuclear fusion in their cores. Every second, stars convert matter into energy through reactions so extreme that replicating them on Earth requires highly specialized machines, careful shielding, and scientists who deserve more snacks than they probably receive. Our own Sun, for example, emits around 3.8 times 10 to the 26th power watts of power every second. That number is so large it behaves less like a fact and more like a dare. And the Sun is considered fairly ordinary. Some stars are much larger, hotter, brighter, and shorter lived. Some pulse, some flare, some spin rapidly. Some are nearing ends that will involve collapse or explosion. They only appear peaceful because they are very far away, and because your eyes cannot see the constant storm of particles, magnetic fields, and radiation involved. Even sunlight arriving on your skin is evidence of a star being energetically active. It just happens to reach us in a particularly friendly format. Then there is motion. The Earth spins at roughly 1,670 km per hour at the equator. It orbits the Sun at about 107,000 km per hour. The solar system orbits the centre of the Milky Way at around 800,000 km per hour. The Milky Way itself moves relative to nearby galaxies, while the universe expands on larger scales. At no point are you actually sitting still. You may feel motionless in bed, on a sofa, or in a chair listening quietly, but you are currently participating in several simultaneous cosmic journeys at impressive speed. It simply does not feel dramatic, because everything around you is moving with you. This is one of the universe's favourite tricks. When motion is shared, it feels like rest. A passenger on a smooth train can sip tea comfortably while travelling quickly. Likewise, we drift through space wrapped in local calm, barely noticing the velocity. Now let us widen the view. Those stars we see as points are separated by vast distances. Light from many of them began travelling before you were born. Some before your grandparents were born. Some visible objects in the night sky are so distant that the light reaching Earth tonight began its journey when human civilization looked very different indeed. This means the sky is not only active, but delayed. We do not see the universe as it is right now. We see it as it was when light left each source. A nearby star may appear as it was years ago. A distant galaxy may appear as it was millions or billions of years ago. In some cases, the object we are observing may have changed dramatically or even ceased to exist in the time since its light departed. So the calm sky is not a live broadcast. It is an archive. That alone is wonderfully strange. We look upward for stillness and receive history instead. Now, let us talk about emptiness, because space often gets described as empty. It is true that compared with earthly environments, much of space is sparse. But sparse does not mean inactive. Interstellar space contains gas, dust, magnetic fields, radiation, wandering objects, shock waves from old explosions, and particles moving at extraordinary speeds. Entire clouds, larger than solar systems, drift and collapse under gravity. Regions that look dark may be nurseries where future stars are slowly forming. Other regions are remnants of ancient stellar death still expanding outward. Empty, in cosmic terms, usually means there is a room to cause trouble. Take a nebula, for example. Seen through telescopes, a nebula may look like a tranquil cloud, colourful and suspended. Beautiful, yes. Peaceful, not necessarily. Many nebulae are shaped by harsh ultraviolet radiation, violent stellar winds, shock fronts, and past explosions. Gas is compressed, ionized, heated, and pushed into new forms. The result is lovely. The process is rough. This pattern repeats often in astronomy. What looks graceful from afar may be the product of intense forces. Now consider galaxies. From a distance, spiral galaxies appear elegant and balanced, their arms curving smoothly through space. Elliptical galaxies look like soft glows. Irregular galaxies resemble abstract art made by someone with access to gravity. Yet inside galaxies, stars are born and die constantly. Black holes feed in some centres. Clouds collide. Radiation pours outward. Orbits continue. Occasionally galaxies interact with neighbours, stretching one another with tidal forces over millions of years. A galaxy can look calm the way an ocean looks calm from an airplane. Perspective matters. If you have ever seen the sea from high above, it can resemble blue stillness. Closer down, waves rise, currents pull, storms churn, and countless lives move within it. The universe behaves similarly. Distance smooths complexity into serenity. There is another reason cosmic violence hides well. Human senses are narrow tools. We see a thin band of visible light. We do not naturally detect radio waves, infrared heat signatures, ultraviolet radiation, X-rays, gamma rays, neutrinos, or gravitational waves. Yet much of the universe expresses itself through exactly these channels. Without instruments, we miss most of the conversation. A black hole feeding actively may blaze in X-rays. A cold dust cloud glows in infrared. Pulsars emit radio pulses. Merging compact objects shake spacetime itself. None of this is obvious to the unaided eye. The night sky can seem silent because we are listening through a keyhole. Modern astronomy changed that. Once we built radio telescopes, X-ray observatories, space telescopes, neutrino detectors, and gravitational wave instruments, the calm universe became far more animated. Suddenly we found jets blasting from galactic centres, stars flaring violently, bursts of gamma radiation from distant cataclysms, and collisions detectable through ripples in reality itself. It was rather like discovering that a quiet library is actually full of people communicating through methods you had never learned. Even our own sun, familiar and dependable, becomes more dramatic under different instruments. Visible light shows a bright disk. Other wavelengths reveal loops of magnetized plasma, eruptions, sunspots, coronal mass ejections, and outer layers far hotter than common sense first expects. Space weather from solar activity can affect satellites, communications, and power systems here on Earth, so even the nearest star has moods. Thankfully, most are manageable by cosmic standards. Now imagine standing on a hypothetical planet orbiting a red dwarf star known for flares. The sky might seem normal one day, and then suddenly unleash bursts of radiation capable of transforming atmospheric chemistry or stressing potential life. Around some stars, calm and danger may alternate routinely. Our sense of peaceful skies is partly local privilege. Earth benefits from a relatively stable star, a magnetic field, and an atmosphere that helps shield life. Not every world is so fortunate. Then there are timescales. Human lives are brief compared with cosmic processes. Mountains rise and erode slowly enough that we think of them as fixed. Likewise, stars evolve slowly enough that they seem eternal. But if one could watch the sky over millions of years, constellations would deform, stars would ignite and fade, galaxies would dance, and explosive events would punctuate the darkness regularly. The universe is dynamic. We are simply observing from a short bench interval. Think of watching a forest for 10 seconds. You might conclude nothing happens there. Watch for years, and you see seasons, growth, decay, migrations, storms, births, deaths, fires, recovery. Duration reveals truth. The same applies to the cosmos. There is also hidden tension in many systems. A star can appear stable, while pressure in its core slowly changes composition. A binary pair may seem quiet while losing energy and spiralling inward. Matter around a black hole can orbit peacefully until a threshold triggers instability. Magnetic fields can twist gradually before snapping in sudden releases. This is the quiet before chaos. Energy can be stored invisibly for ages. Then balance fails. Humans know this pattern too. Weather fronts build before storms. Fault lines strain before earthquakes. Personal stress accumulates before one misplaced spoon becomes strangely emotional. Nature often prefers build-up followed by release. The universe simply works with larger equipment. One of the most humbling examples is the star Betelgeuse, a red supergiant in the constellation Orion. To casual eyes, it's a bright reddish star, familiar and calm, yet it is a massive aging star expected someday to explode as a supernova. Someday in astronomy can mean tomorrow, or 100,000 years from now, which is one reason astronomers sometimes appear patient. When it finally happens, if humanity is around to witness it, it could shine brightly in Earth's sky. For now it twinkles politely. That contrast is everywhere in the heavens. Calm surfaces, hidden futures. And perhaps that is one reason stargazing can feel so soothing. It offers stillness without requiring actual stillness. The sky does not need to be inactive to be calming. It only needs to be vast enough that activity arrives softened by distance. A thunderstorm next door may be stressful. A supernova 50 million light-years away can be restful to contemplate. Scale transforms experience. There is also comfort in knowing that violence in the universe is mostly indifferent to us. It is not aimed. It is not personal. Black holes are not thinking about your schedule. Gamma-ray bursts are not evaluating your recent decisions. Galaxy mergers are not commentary on your inbox. Cosmic events happen because conditions allow them. Meanwhile, here you are, in a room or a bed or a quiet space, borrowing perspective from distant things. That can be grounding. Your concerns matter, of course, but they exist inside a reality so broad and active that no single worry needs to occupy the whole stage tonight. The sky above may look calm, yet beneath that appearance lies motion beyond measure. And perhaps the reverse is true within us sometimes. We may look composed while carrying internal storms. Seeing one can help with the other. So when you next glance upward and see a peaceful field of stars, remember gently that peace and activity are not opposites. The universe is full of blazing furnaces, racing worlds, collapsing cores, expanding remnants, and forces gathering strength in silence. Look up at the stars and it is easy to imagine them as permanent fixtures. They seem dependable, reliable, calm. Night after night they return, holding their places with admirable discipline, as if the sky were managed by an exceptionally organised caretaker. A few shift with the seasons, some twinkle more than others, and occasionally clouds interfere with the schedule, but stars themselves appear steady. They look like things that simply continue, yet stars are not eternal. They are living through long physical stories. They are born, they change, they age, and some of them end in explosions so immense that for a short time they can outshine entire galaxies. This is the story of supernovae. And despite the dramatic name, the process often begins with something surprisingly ordinary: balance. A star exists because two forces oppose one another. Gravity pulls inward, trying to compress the star into a smaller, denser object. At the same time, the heat and pressure generated by nuclear fusion in the core push outward. As hydrogen atoms fuse into helium, energy is released. That outward pressure resists collapse. For most of a star's life, these forces remain in a workable compromise. Gravity says inward, fusion says no. The result is stability. Our own sun is in this phase now, and it has been for billions of years. Every second, it quietly converts matter into energy, lights the solar system, supports life on Earth, and generally behaves like a competent middle manager of planetary affairs. But not all stars live identical lives. The most massive stars burn fuel much faster than smaller ones. They shine brighter, live shorter lives, and spend their existence racing through resources with the urgency of someone who mistakes snacks for a long-term investment plan. Mass changes everything. A small red dwarf may burn gently for trillions of years. A giant blue star may last only millions. The larger the star, the more violently it tends to conclude matters. To understand a supernova, imagine a star nearing the end of its available fuel. Hydrogen becomes scarce in the core, so fusion shifts to heavier elements. Helium may fuse into carbon, carbon into neon, neon into oxygen, oxygen into silicon. In very massive stars, this chain continues until iron forms in the core. Iron is a problem. Fusion of lighter elements releases energy. Fusion of iron does not help in the same way. It consumes rather than provides usable support. Once a massive star builds an iron core large enough, the engine that held gravity back begins to fail, and gravity has been waiting patiently. When outward pressure drops, the core collapses inward with astonishing speed. Matter rushes down, temperatures soar, electrons and protons are crushed together into neutrons. The core compresses so violently that in some cases it becomes a neutron star, an object so dense that a spoonful of its material would outweigh mountains. Then comes the rebound. Infalling outer layers slam into the suddenly stiffened core. Shockwaves surge outward. Neutrinos flood through the star. The outer layers are blasted into space in a titanic explosion. That is a core collapse supernova. For a star that may have lived millions of years, the decisive ending happens in seconds. There is something almost theatrical about that contrast. Ages of shining, then an abrupt finale bright enough to announce itself across galaxies. But of course, the universe does not do theatre, it does thermodynamics. Now let us slow down and consider scale. A supernova can briefly radiate more energy than our sun will emit over its entire lifetime. It may become brighter than the hundreds of billions of stars in its host galaxy combined, at least for a short while. That sentence sounds exaggerated until you remember that stars are enormous reactors, and galaxies contain many of them. Yet even against that backdrop, a supernova can dominate the light. Imagine lighting a candle in a room full of candles, and somehow making yours brighter than all the others together. That would be notable. Astronomers throughout history certainly noticed. Long before telescopes, people recorded new stars appearing suddenly in the sky. These were often supernovae in our own galaxy. In 1054 CE, observers in China and elsewhere documented a bright star visible in daylight for weeks. That event created what we now call the Crab Nebula, a glowing remnant still expanding today. The star seemed to appear from nowhere. In reality, it had died long before. Its light simply arrived then. This is one of astronomy's recurring themes. What feels sudden may be ancient news delivered late. Another famous event was observed by Johannes Kepler in 1604. The Kepler supernova was the last clearly observed supernova in the Milky Way visible to the naked eye. It startled skywatchers because stars were supposed to be fixed and changeless according to older ideas. Then one of them exploded publicly. Science progresses well when reality ignores assumptions. Now, not all supernovae come from massive stars collapsing. Some arise through a different route entirely, involving white dwarfs. A white dwarf is the dense remnant left behind when a sun-like star sheds its outer layers. Left alone, it can cool quietly for immense spans of time. But if it has a nearby companion star, things may become complicated. Matter can be pulled from the companion onto the white dwarf. If enough mass accumulates, the white dwarf may approach a critical limit known as the Chandrasekhar limit. Beyond that threshold, stability fails. Carbon fusion can ignite rapidly throughout the star. Because white dwarfs are already compact and supported by quantum effects rather than ordinary gas pressure, the ignition can run away catastrophically. The entire star detonates. This is called a Type 1a supernova. Unlike core collapse supernova, which often leave neutron stars or black holes, Type 1a events can completely destroy the white dwarf. No central remnant remains. It is a total departure. There is something almost administrative about that outcome. File closed, no forwarding address. Type 1. A supernovae are especially useful because they reach fairly consistent brightness. Astronomers use them as standard candles to estimate cosmic distances. In fact, observations of distant Type 1a supernovae helped reveal that the expansion of the universe is accelerating, leading to the concept of dark energy. So stars exploding have helped us understand the fate of the cosmos. Quite an afterlife for a dead star. Now if a supernova occurred close enough to Earth, it could pose risks. Radiation and energetic particles from a nearby event might affect the atmosphere, perhaps damaging ozone or influencing climate and biology. Fortunately, there are no known stars poised to explode dangerously near us in the immediate future. The universe contains many hazards, but it is usually courteous enough to place them far away. That distance allows us to appreciate beauty rather than panic, and supernova remnants are beautiful. After the explosion, ejected material expands into surrounding gas. Shockwaves heat matter until it glows. Magnetic fields shape filaments. Colours emerge in telescope images depending on elements and wavelengths observed. The Crab Nebula resembles tangled lace made of light. The Veil Nebula stretches like delicate smoke. Cassiopeia A glows as a chaotic shell from a more recent stellar death. These structures are grave markers and nurseries at once. The expelled elements enrich interstellar space. Future clouds may collapse into new stars and planets containing atoms forged in the dead star's core or in the explosion itself. Iron in your blood, calcium in bones, oxygen you breathe. Much of it came from stars and some from stars that exploded. This means supernovae are not merely endings, they are redistribution events. The universe is fond of recycling, though its methods can seem energetic. Let us also mention sound, because many people imagine a supernova as a deafening blast. In space there is no air to carry ordinary sound across vacuum. The explosion itself is silent to distant observers, yet silent does not mean gentle. Light races outward. Particles accelerate. Shockwaves move through gas where gas exists. Space telescopes detect emissions across the spectrum. Instruments register consequences. The loudest things in the universe often happen without noise. That contradiction never gets old. Modern astronomy now detects supernovae routinely in distant galaxies. Robotic surveys scan the sky nightly, comparing images to find new bright points where none were before. Once found, telescopes around the world study them. Brightness curves, spectra, chemical signatures, host galaxies, remnant evolution. Somewhere tonight, while cities sleep and alarms are mercifully postponed, a star may be ending in another galaxy, and software is politely informing astronomers that something dramatic has occurred. There are even superluminous supernovae, rarer events brighter than typical supernovae by large factors. These may involve exotic mechanisms such as rapidly spinning magnetars injecting energy, or unusual interactions with dense surrounding material. In astronomy, whenever something already extreme proves insufficient, nature occasionally provides an upgraded version. Then there are pair instability supernovae, theorized for extremely massive stars. In such stars, energetic photons in the core can convert into electron-positron pairs, reducing pressure support and triggering collapse, followed by explosive burning so powerful the star may be completely disrupted. No remnant, just debris and astonishment. Again, the cosmos has range. What can supernova teach us beyond stellar mechanics? First, that stability is temporary but meaningful. A star can spend most of its life in balance, and that balance sustains worlds. Endings do not erase the long usefulness that came before. Second, stored energy matters. Massive changes often begin invisibly, deep in hidden cores where conditions gradually shift. Third, destruction can create possibility. Without exploding stars, the universe would contain far fewer heavy elements, and rocky planets like Earth might be rare or absent. That includes listeners, pillows, blankets, headphones, and the ability to become sleepy while hearing about thermonuclear catastrophe. Perspective is generous that way. If you ever feel small beneath the night sky, remember that small things can be made from grand histories. You're assembled from matter processed through ancient stars, some of which ended violently enough to scatter their contents across space. You are, in a calm and practical sense, recycled stardust with responsibilities. After learning that stars can end their lives in explosions bright enough to rival galaxies, it might seem only fair to pause there and declare the contest settled. Surely a supernova is dramatic enough. Surely the universe has made its point. Surely no further escalation is necessary. The universe, unfortunately for our sense of moderation, disagrees. Because beyond supernovae lies another category of events so intense, so concentrated, and so startling when first discovered that astronomers initially had no idea what they were seeing. These are gamma-ray bursts, often shortened to GRBs, and for brief moments they can become the brightest known explosions in the observable universe. That sounds like marketing language, but in this case it is mostly just statistics trying to keep up. To understand why gamma-ray bursts cause such confusion, we should begin with gamma-rays themselves. Light comes in many forms. The visible colours our eyes detect are only a narrow slice of a much wider electromagnetic spectrum. There are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Gamma rays occupy the highest energy end of that spectrum. They are associated with the most energetic processes known. If visible light is a candle, and X-rays are a welding torch, gamma rays are the sort of thing that makes engineers quietly step backward. Earth's atmosphere blocks most gamma rays, which is fortunate for life and mildly inconvenient for astronomy. To study them properly, we needed instruments in space. That is where the story takes a delightfully strange turn. During the Cold War, the United States Department of Defense launched satellites called Vela to detect gamma radiation from possible clandestine nuclear weapons tests in space or the atmosphere. These satellites were not designed to solve cosmic mysteries. They were designed to make sure no one was cheating on treaties. Instead, in the late 1960s, they detected bursts of gamma rays coming not from Earth, but from deep space. Imagine building a smoke detector and discovering dragons. The signals were brief, irregular, and clearly extraterrestrial. They did not match known solar activity. They did not repeat from the same direction in any obvious pattern. They appeared suddenly, then vanished. For years, they remained one of astronomy's most tantalizing puzzles. What could create such flashes? The bursts lasted anywhere from milliseconds to minutes. Some were short and sharp, others lingered longer. Their energies, once distances were later understood, proved staggering. For a time, scientists did not know whether these events were relatively nearby, perhaps within our galaxy, or fantastically distant. That distinction mattered enormously. A candle nearby and a lighthouse far away can appear similarly bright, but imply very different realities. Eventually, better instruments and careful observations showed that gamma-ray bursts come from distant galaxies, often billions of light years away. That changed everything. Because if something that far away still appears detectable across the cosmos, then the true event must be unimaginably powerful, and it is. For a few seconds, some gamma-ray bursts release as much energy as the Sun will emit over its entire lifetime of roughly 10 billion years. Not all invisible light, of course, but concentrated in high-energy radiation and accompanying outflows. The numbers become almost impolite. Now it helps to know that gamma-ray bursts are not one single phenomenon. Broadly speaking, they come in two main families: long-duration bursts and short-duration bursts. Long bursts last more than about 2 seconds, though many continue much longer. They are linked to the deaths of massive stars collapsing into black holes. In certain cases, when the core of a rapidly rotating massive star collapses, it forms a black hole or neutron star and launches narrow jets of material moving close to light speed. If one of those jets happens to point toward Earth, we detect an intense gamma-ray burst. This is important. The explosion is not necessarily equally bright in all directions. Much of the energy is beamed into jets, like cosmic spotlights. If you're outside the beam, the event may look less dramatic or escape notice entirely. So some gamma-ray bursts are not only powerful but directional. The universe occasionally uses focus. The second family, short-duration bursts, usually lasting less than 2 seconds, are now strongly associated with mergers of compact objects such as neutron stars. Two neutron stars can orbit one another for millions or billions of years, slowly losing energy through gravitational waves, spiraling inward until they finally collide. When they do, the result can be a short gamma-ray burst, along with gravitational waves and heavy element production. We will revisit neutron star collisions later, because they deserve their own careful attention. They're among the most extraordinary events ever confirmed. For now, let us stay with brightness. Gamma-ray bursts are often followed by something called an afterglow. Once the initial flash fades, the jets interact with surrounding gas, producing emissions in X-rays, visible light, radio waves, and other wavelengths. These afterglows can linger for days, weeks, or longer. That afterglow proved crucial. By studying it, astronomers could pinpoint host galaxies, measure distances, and finally understand that these bursts were happening across the universe. A mystery became a measurable phenomenon. Science often progresses this way. First confusion, then instrumentation, then charts. One especially famous event occurred in 1999, GRB 990123. Its optical afterglow became bright enough to be detected by small telescopes, even though it happened billions of light years away. This was astonishing. Imagine seeing a match strike on another continent. Then came later events that stretched expectations further. In 2008, GRB 080319b was briefly visible to the naked eye under dark skies, despite originating billions of light years away. For a short time, one of the brightest things visible in the sky was an explosion from the deep past of a distant galaxy. That is difficult to emotionally process. Something happened before modern humans existed in anything like current form. Its light travelled for billions of years. Then one night it reached Earth, and could, in principle, be seen by human eyes. The universe has excellent timing and no concern for our calendars. Now let us talk about what it would feel like nearby. The answer is simple and reassuring. We do not plan to test it. A gamma ray burst close enough and pointed directly at Earth could be dangerous. High-energy radiation might damage the atmosphere, deplete ozone, and trigger ecological consequences. Some scientists have explored whether past mass extinctions could conceivably involve such astrophysical events, though direct evidence is difficult. Fortunately, space is vast, gamma-ray bursts are rare nearby, and jet orientation matters. The universe contains many hazards, but probability usually keeps them at polite distances. Still, it is humbling to know such things exist. Imagine an event so energetic that if aimed improperly, it could affect a planet from thousands of light years away. And yet most gamma-ray bursts never trouble us. They occur unseen by unaided eyes, registered only by satellites and telescopes. Their violence is mostly academic, which is ideal. There is another reason gamma-ray bursts fascinate scientists. They act like flashlights shining through the early universe. Because they are so bright, their light can travel immense distances. As it passes through intervening gas clouds and galaxies, it carries signatures of those materials. By analysing burst afterglows, astronomers can study conditions in the distant past. So these catastrophic blares also become tools. Nature often pairs drama with utility. Some of the farthest known objects ever studied in detail were observed through gamma-ray burst afterglows. In that sense, dying stars and compact mergers help illuminate cosmic history. That is unexpectedly generous. The mechanisms behind GRBs also involve some of the fastest material known. Jets launched during these events move at speeds extremely close to light speed. At such velocities, relativity becomes essential. Time, energy, and observed brightness depend on motion in ways Newton would likely have found educational. Matter in these jets plows into surrounding material, creating shocks that accelerate particles and produce radiation across wavelengths. Magnetic fields, turbulence, and particle physics all join the performance. This is not a simple explosion. It is an orchestra of extremes, and yet from Earth, it begins as a tiny spike on a detector. There is something lovely in that contrast. The grandest violence can arrive as a subtle line on a graph, waiting for someone awake in a control room to notice. Gamma-ray bursts also remind us how narrow ordinary experience is. We think of bright things in visible terms: sunlight, lamps, lightning, fire. But some of the brightest events in the universe are brightest in forms of light our eyes cannot see. Reality exceeds intuition regularly. If human vision included gamma rays, the sky would look very different and daily life would likely be less relaxing. Thankfully, evolution selected a more peaceful operating mode. Now, if you compare supernovae and gamma-ray bursts, which is more violent? It depends on the metric. Supernovae can release immense total energy and physically unmake stars. Gamma-ray bursts can concentrate astonishing energy into narrow jets and outshine nearly anything else briefly. Some long GRBs are associated with special types of stellar collapse beyond ordinary supernova behaviour. In truth, categories overlap. The universe dislikes clean filing systems. What matters more is that gamma-ray bursts represent nature operating near the limits of what matter, gravity, and relativity can arrange. They are warnings that scale has no upper courtesy setting. There is also a quieter lesson. Many gamma-ray bursts begin with long periods of hidden preparation. A massive star spends millions of years evolving before collapse. Two neutron stars spiral together for ages before merging. The spectacular moment is brief, but the setup is ancient. That pattern appears everywhere. Sudden outcomes often have slow causes. Storms gather before rain. Forests grow before fires. Civilizations build before headlines. Stars age before detonations. The burst is only the visible part. Perhaps that idea can be calming. Not every intense moment is random. Often it is the release of conditions long in the making. Understanding the build-up helps explain the flash, and if tonight your own mind feels busy, restless, charged with thoughts, there is comfort in remembering that human tension can also be eased gradually, long before any dramatic release becomes necessary. No gamma rays required. After the brief fury of gamma ray bursts, it is time to slow down and focus on something smaller, denser, and in many ways even stranger. Imagine taking a star, removing most of its outer layers, crushing the core with such force that ordinary atomic structure gives up, and leaving behind an object only about the size of a city. Then give that object more mass than the Sun, spin it rapidly, and place it in orbit with another object just as extreme. Now let them circle each other for millions or billions of years. Eventually they meet. This is the story of colliding neutron stars, one of the most remarkable violent events ever observed. It combines gravity, relativity, nuclear physics, cosmic chemistry, and the sort of dramatic timing the universe seems unwilling to stop using. To appreciate the collision, we should first understand the objects themselves. A neutron star is what can remain after a massive star ends its life in a supernova. If the collapsing core is not heavy enough to become a black hole, gravity compresses it into something astonishingly dense. Electrons and protons are squeezed together, forming neutrons. Matter is packed so tightly that a teaspoonful, if you could somehow transport it safely and ignore several practical concerns, would weigh billions of tons on Earth. That is not a typo. A mountain's worth of mass can fit into something you could walk across in an afternoon, assuming the surface conditions did not immediately end the walk. Neutron stars are typically around 20 kilometers across, give or take, yet they may contain more mass than our Sun. Their gravity is immense. Their magnetic fields can be enormous. Some rotate many times per second, sweeping beams of radiation through space like celestial lighthouses. When we detect those pulses, we call them pulsars. So already, a single neutron star is an exotic object. Two of them together are a long-term plan for excitement. Many stars form in binary systems, pairs orbiting one another. If both stars are massive enough, each may eventually explode and leave behind a neutron star. If the system survives those supernovae without being torn apart, the two remnants continue orbiting. At first, they may be widely separated, but according to Einstein's general relativity, accelerating masses can emit gravitational waves, ripples in space-time itself. As the neutron stars orbit, they lose orbital energy through these waves. That loss is tiny at first, but tiny changes given enough time become large outcomes. Orbit after orbit, century after century, the stars draw closer. Their dance tightens. Their speed increases. The period of each orbit shrinks. A pair that once took hours to circle may later take minutes, then seconds, then fractions of seconds. Imagine two objects more massive than the Sun, each only city-sized, whipping around each other hundreds of times per minute while warping reality. This is not an everyday traffic situation. The final moments are extraordinary. As the neutron stars spiral inward, tidal forces distort them. Matter can be torn loose. Magnetic fields twist violently. Space-time ripples intensify. Then the stars collide and merge in a fraction of a second. Depending on their combined mass, the result may be a heavier neutron star, at least briefly, or a black hole surrounded by hot debris. Either way, the event releases immense energy. We can detect it in several forms: gravitational waves, gamma rays, visible light, X-rays, radio waves, and the expanding aftermath. This is known as multi-messenger astronomy, which is a very elegant phrase meaning the universe sends several kinds of evidence at once. One of the most famous scientific moments of the 21st century came on August 17th, 2017. The LIGO Scientific Collaboration and Virgo Collaboration detected gravitational waves from a neutron star merger catalogued as GW170817. About 1.7 seconds later, space telescopes observed a short gamma ray burst from the same region. Soon afterward, observatories around the world found the optical afterglow in a galaxy about 130 million light-years away. This was historic. For the first time, humanity clearly observed a neutron star collision through both gravitational waves and traditional light. We did not merely see the event, we felt the ripple and saw the flash. It was as if the cosmos sent both a letter and a phone call. Why was that so important? Because it confirmed long-standing theories about the source of short gamma-ray bursts. It tested relativity under extreme conditions, it improved estimates of cosmic expansion methods, and it solved another deep mystery. Where many heavy elements come from: gold, platinum, rare earth elements. For years, scientists debated how the universe forges some of the heaviest elements. Ordinary stellar fusion does not easily produce them. Supernovae may contribute some, but neutron star mergers turned out to be major factories. In the merger debris, matter is flooded with neutrons under extreme conditions. Atomic nuclei rapidly capture those neutrons in a process called the R process, building heavy elements quickly. So when neutron stars collide, they do not merely destroy and merge, they manufacture treasure. Jewelry has surprisingly violent origins. That ring, necklace, or electronic component containing precious metals may owe some atoms to ancient stellar corpses crashing together long before Earth existed. There is something wonderfully humbling in that. Now let us consider brightness. The visible glow from a neutron star merger is called a kilonova. It is brighter than a nova, dimmer than many supernovae, but still powerful. The name comes from being roughly 1,000 times brighter than a classical nova. As radioactive, freshly formed elements decay in the ejector, the debris glows, colours shift over time. Infrared light becomes especially important as heavy elements influence opacity. Telescopes study these changes to infer composition and physics, so even after the collision, the story continues. Debris expands, light evolves, radio waves emerge as ejecta slam into surrounding gas. Months and years later, scientists still learn from the aftermath. Now, if you are wondering what it would be like nearby, the answer is again reassuringly theoretical. Very nearby would be unfortunate. Radiation, energetic particles, and gravitational disturbances from a close merger could pose serious hazards. But such events are rare and usually far away. Space remains vast and mostly considerate in matters of direct exposure. This distance allows us to appreciate the science rather than make emergency plans. There is another fascinating aspect to neutron star mergers. They test matter at densities impossible to recreate fully in laboratories. What is inside a neutron star? Mostly neutrons, yes, but perhaps with exotic states of matter in deeper layers. Quark matter, superfluid components, strange interactions under crushing pressure. When neutron stars collide, their behaviour carries clues. How they deform before merger, how long a remnant survives, what waves they emit, what debris escapes, all help physicists understand matter under conditions beyond normal intuition. So these events are not only violent, they are informative. Nature's most dramatic episodes often double as experiments no institution could afford to build. Let us pause with the scale again. 2 objects each heavier than the Sun, only about city-sized, orbiting faster and faster, releasing measurable ripples in space-time detectable on Earth, producing gold and platinum, possibly forming a black hole, all in one event. The universe can be impressively efficient when motivated, and yet from far away, none of this is loud. No crash reaches us through vacuum, no thunder rolls across galaxies. Instruments register tiny distortions, spikes in radiation, changing spectra, fading light. The loudest collisions can arrive as subtle signals. That contradiction remains one of astronomy's most charming habits. There is also something quietly moving about the timescales involved. Two neutron stars may spend billions of years approaching their final meeting. Civilizations rise and fall while they orbit. Continents shift. Species evolve. On Earth, countless histories unfold. Meanwhile, elsewhere, two dead stars continue their patient inward spiral. Then in an instant, they merge. Long preparation, brief climax, lingering consequences. This pattern appears often enough to feel almost universal. We see it in geology, weather, biology, and human life. Slow pressures gather, then release. The visible moment is short, but its roots run deep. If your own mind ever feels as though things happen suddenly, it can help to remember that sudden moments are often preceded by long unseen processes. Understanding the build-up softens the shock. Neutron star mergers also remind us that endings can combine into beginnings. Each neutron star is already the remnant of a dead massive star. Yet when two remnants meet, they create new elements, new signals, new understanding. Even leftovers can become origins. That is not only astrophysics, it is occasionally useful philosophy. Now, one may ask whether colliding neutron stars are more violent than gamma-ray bursts or supernovae. The answer, as always, depends on the metric. In total visible brightness, perhaps not always. In density, compactness, relativistic conditions, gravitational wave significance, and element production, they are extraordinary contenders. Ranking cosmic violence is a little like ranking weather, by whether you prefer tornadoes, volcanoes, or tsunamis. Categories help, but none are ideal vacations. Still, neutron star mergers hold a special place because they unite so many extremes at once: gravity, density, speed, nuclear physics, light, waves, and creation through destruction. Sometimes collapse goes further. Sometimes no neutron star remains. Sometimes gravity wins completely, producing an object from which not even light escapes. By the time we arrive at black holes, the universe has already shown off considerably. We have watched stars explode with enough brightness to rival galaxies. We have seen neutron stars collide, sending ripples through space-time and forging precious metals in the wreckage. We have discussed gamma-ray bursts so intense they can outshine almost everything else for brief moments, and yet black holes still manage to feel like the final boss of astrophysics. Part of that reputation comes from the name. Black hole sounds less like a scientific term and more like something you're advised not to approach in a warning video. It suggests darkness, danger, disappearance, and regrettable decisions. In fairness, those associations are not entirely misplaced. But black holes are not cosmic vacuum cleaners roaming the universe, hungrily inhaling everything nearby with villainous enthusiasm. They are stranger, more elegant, and in some ways more ordinary than popular imagination allows. At their core, black holes are objects where gravity has become overwhelming. That is the essential story. If enough mass is compressed into a small enough region, the escape velocity from that region exceeds the speed of light. Since nothing with mass can travel faster than light, and light itself cannot escape once past a certain boundary, that region becomes effectively hidden from the outside universe. The boundary is called the event horizon. Cross it inward and no message returns. This is the part that gives black holes their mystique. Not because they are magical portals or bottomless drains, but because information from inside the horizon cannot reach outside observers in the usual way. They are not holes in the sense of empty tunnels. They are places where matter has collapsed into an extreme state governed by gravity. So why call them crushers? Because they represent gravity winning completely. For a normal star, outward pressure from fusion resists collapse. For white dwarfs, electron degeneracy pressure helps support the remnant. For neutron stars, neutron degeneracy pressure and nuclear forces hold against gravity, at least up to a limit. Past that limit, gravity says thank you very much and continues inward. When enough mass is concentrated, no known pressure can stop further collapse. A black hole forms. Now, there are several kinds. Stellar mass black holes form from the deaths of massive stars. They may contain a few times the mass of our Sun, or dozens of solar masses, packed into a region surprisingly small compared with the star that created them. Then there are intermediate mass black holes, still somewhat mysterious and harder to confirm, bridging the gap between stellar and supermassive scales, and at the centres of many galaxies, including our own Milky Way, reside supermassive black holes containing millions or billions of solar masses. These are the giants. Our galaxy's central black hole is Sagittarius, a star, containing roughly 4 million times the mass of the Sun. It is far away and presently rather quiet by cosmic standards, which is considerate. Other galaxies host black holes so large that if placed where our Sun is, their influence would extend beyond the orbit of Mercury, Venus, Earth, perhaps farther depending on the example chosen. And yet, size alone is not what makes black holes violent. A black hole sitting alone in empty space is mostly just gravity with excellent boundaries. If the Sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting nearly as before, though the lighting situation would deteriorate sharply. Mass determines gravitational pull at distance, not the label attached to the object. The violence comes when black holes interact with matter. Imagine gas, dust, or an unlucky star wandering too close. Matter falling directly inward is possible, but often it has angular momentum, so instead it spirals around the black hole, forming an accretion disk. This disk is where things become dramatic. Material in the disk rubs, compresses and heats as inner regions orbit faster than outer ones. Temperatures soar to millions of degrees. Friction and magnetic effects convert gravitational energy into radiation. The region around a feeding black hole can become one of the brightest sources in the universe, not the black hole itself, the chaos around it. This distinction is worth savouring. Black holes are dark, but their dining habits can be luminous to an unreasonable degree. In some systems, especially when a stellar mass black hole feeds from a companion star, we detect intense X-rays. In galactic centres, supermassive black holes devouring gas can power quasars and active galactic nuclei, bright enough to outshine entire galaxies. So one of the darkest things known can create some of the brightest phenomena known. The universe enjoys irony. Now let us discuss tidal forces, because this is where the phrase cosmic crusher earns its title more directly. Gravity weakens with distance. Near a black hole, the difference in pull between your nearer side and farther side can become extreme. If you fell feet first toward a sufficiently small black hole, your feet would be pulled more strongly than your head. The result is stretching. Physicists charmingly call this spaghettification. Science, even at its most serious, occasionally names things like a child with excellent instincts. You would be stretched lengthwise and compressed sideways. This would be educational only briefly. For supermassive black holes, interestingly, tidal forces at the horizon may be gentler, because the horizon lies farther from the concentrated centre. One might cross the event horizon of a sufficiently large black hole without immediate dramatic stretching, though later prospects remain poor. So even danger in black holes has scale-dependent nuance. Then there are stars that pass too close. Sometimes a star wanders near a supermassive black hole, and tidal forces tear it apart. Gas from the shredded star forms a bright flare as it falls inward. These are called tidal disruption events. The phrase sounds clinical. The reality is that a star is unmade by gravity and partially eaten, while the galaxy briefly lights up. Astronomy often uses calm language for outrageous behaviour. Now, black holes also spin. A rotating black hole drags nearby spacetime around with it, an effect predicted by general relativity called frame dragging. Space itself, in a sense, is stirred by rotation near the hole. This matters because spinning black holes can help launch jets, narrow beams of particles and energy shooting outward from regions near the poles at near-light speed. These jets can extend for thousands or even millions of light years in large systems. Imagine something smaller than the solar system helping power beams longer than galaxies. That is the sort of scale mismatch black holes specialize in. Jets plow into surrounding gas, heating it, shaping galaxy environments, and regulating future star formation. In this way, black holes can influence entire galaxies. A central black hole is not merely a resident, it can become an urban planner. Now let us return to what we mean by violence. Black holes may not always explode in the way stars do, but they excel in concentration of force. They convert gravitational potential energy with astonishing efficiency. They crush matter into extreme states. They distort time and space. Yes, time too. According to relativity, clocks near strong gravity run more slowly relative to distant clocks. Near a black hole, this effect becomes profound. To a distant observer, infalling processes can appear slowed near the horizon. To the infalling traveller, personal time continues normally until circumstances become less narratively convenient. So black holes do not only crush matter, they complicate timekeeping, which, if we're honest, many people manage without needing one. There is also a common misconception that black holes endlessly grow by swallowing everything nearby. In truth, many are quiet for long periods because space is large and matter is not always conveniently delivered. Feeding requires supply. Some black holes are dormant giants, sitting in galactic centres with little on the menu. Even monsters need logistics. Our own Sagittarius A star is comparatively faint right now. Evidence suggests it may have been more active in the past. Galaxies, like cities, have busy eras and quieter ones. Modern astronomy has even imaged black holes indirectly. The Event Horizon Telescope collaboration produced images of the shadow region around M87 star, and later Sagittarius A star. These were not snapshots of a hole itself, but of glowing material around the event horizon and the silhouette created by intense gravity-bending light. Humanity, a species that misplaces keys regularly, managed to image the surroundings of black holes in distant galaxies. That is worth appreciating. There is something calming about black holes too, oddly enough. They are honest consequences, no anger, no intention, no cosmic drama club, just mass, gravity, geometry and equations unfolding precisely. Their terror comes not from malice, but from consistency. Given certain conditions, they must exist. That can feel strangely reassuring. The universe, however wild, is lawful, and black holes remind us that unseen things can shape everything around them. We cannot observe the interior directly, yet we infer presence from motion of stars, jets, radiation, lensing, and waves. Invisible causes, visible effects. Many truths work that way. If your own life feels busy tonight, if thoughts orbit restlessly, consider that not all powerful things need spectacle. Some forces are quiet, some transformations happen in darkness, some centres hold more influence than appearances suggest. The cosmos knows this well. A single black hole is already a difficult thing to behave casually around. It bends light, slows time, swallows matter, and turns nearby gas into blazing radiation if properly supplied. It represents gravity in one of its most concentrated forms. If the universe were making a list of objects not to bump into, black holes would rank highly, and yet, even a black hole can find company. Across the cosmos, there are places where two black holes become bound together in orbit. Perhaps they were once massive stars born as a pair, each living fast, dying violently, and collapsing into black holes while remaining gravitationally linked. Or perhaps they formed separately and later met in dense stellar environments, such as globular clusters or galactic centres, where repeated interactions can bring them together. However it begins, the result is extraordinary. Two invisible objects, each already extreme, circling one another in darkness. No fireworks at first, no dramatic explosion, No obvious flare for distant observers in many cases. Just motion and gravity conducting a long, patient conversation. But it is not a static arrangement. As the pair orbits, they lose energy through gravitational waves, ripples in space-time predicted by Albert Einstein in 1916. Whenever massive objects accelerate asymmetrically, especially in close orbit, they can disturb the geometry of space-time itself. Those disturbances propagate outward at the speed of light. Imagine dropping 2 stones into a pond, except the pond is reality, and the stones are black holes. It is not a perfect analogy, but it is polite enough to get us started. These gravitational waves carry energy away from the binary system. Because energy is leaving, the black holes spiral inward. Their orbit shrinks, they move faster, the waves grow stronger, the process feeds itself. For millions or billions of years, this in-spiral may proceed gradually. Then, in the final moments, everything accelerates. The black holes whip around each other many times per second. Their velocities become substantial fractions of light speed. Space-time near them is violently distorted. The emitted gravitational waves surge in intensity, and then they merge. No crash sound echoes through space. No fireball blooms in vacuum by necessity. Instead, the black holes become one larger black hole, and a portion of their mass is converted directly into gravitational wave energy. This is one of the most astonishing facts in modern science. Mass itself can be radiated away as ripples in space-time. When the first directly detected black hole merger was announced in 2016 by LIGO, it revealed that 2 black holes of about 36 and 29 solar masses had merged into one of about 62 solar masses. You may notice arithmetic tension there. 36 plus 29 equals 65. Where did the missing 3 solar masses go? Into gravitational waves. In a fraction of a second, roughly 3 times the mass of our Sun was converted into energy and carried outward through the universe as distortions of space-time itself. For a brief moment, the power output exceeded that of all the stars in the observable universe combined, though in gravitational waves rather than visible light. That sentence deserves to sit quietly for a moment. The universe can be outrageously dramatic while remaining visually subtle. This first event was named GW150914 after the date of detection, September 14th, 2015. It marked the first direct observation of gravitational waves and the first direct evidence of a black hole binary merger. It was one of the great scientific moments of the century. Why? Because until then, gravitational waves had indirect evidence, but no direct capture. Einstein predicted them, yet even he doubted whether humans would ever measure such tiny distortions. By the time they reached Earth, the changes in length were smaller than a proton over kilometre-scale detectors, and still we measured them. That is worth admiring. A species that struggles with passwords built instruments sensitive enough to detect 2 black holes colliding over 1 billion light-years away. Now, how does one hear a black hole merger? LIGO uses laser interferometers with long perpendicular arms. Passing gravitational waves stretch one arm while compressing the other by minuscule amounts, altering the travel time of laser beams. By comparing signals, scientists can detect the wave pattern. The waveform from inspiraling black holes rises in frequency and amplitude as they approach each other. It becomes a characteristic chirp. Yes, one of the grandest collisions in nature announced itself as a chirp. The universe has an understated sense of humour. This chirp contains information. From it, scientists infer masses, spins, distance, orientation, and properties of the merger. It is less like hearing a noise and more like reading geometry through vibration. Since that first detection, many more black hole mergers have been observed by LIGO, Virgo Collaboration, and later CAGRA. Some involve surprisingly massive black holes. Others challenge assumptions about how such binaries form. Each detection adds a data point to the census of hidden objects. Before gravitational wave astronomy, many black holes were known through their effects on companion stars or active feeding environments. But quiet black holes merging in empty darkness were harder to find. Now we can detect them directly through gravity alone. That changed astronomy permanently. Now let us imagine, carefully and from an impossible safe vantage point, what the final merger might look like. Two regions of darkness circle faster and faster, surrounded perhaps by little visible matter. Light from background stars would be distorted by lensing. Space near them would be profoundly curved. Time itself would behave differently close in. As the horizons near one another, the geometry becomes intensely dynamic. Then the two horizons join, forming one distorted larger horizon that quickly settles into a stable spinning black hole. This settling phase is called ringdown. Like a struck bell vibrating before becoming still, the new black hole emits gravitational waves that damp away as it relaxes. A bell made of spacetime. Again, not a perfect analogy, but charming enough to keep. Now, compared with explosions like supernovae or gamma-ray bursts, black hole mergers can seem oddly clean. There may be little ordinary matter involved. No expanding shell of glowing gas is required. No star need be visibly torn apart at the moment of merger. Much of the energy leaves in a form humans cannot sense naturally, and yet, in terms of sheer power and the fundamental nature of what is happening, these are among the most violent events known. Two warped regions of gravity combine. Mass becomes waves, reality flexes. What more would one like from an extreme event? There are also consequences after merger. The resulting black hole may receive a recoil kick if gravitational waves were emitted asymmetrically. In some cases, the merged object can be launched through space at high speed, potentially even ejected from its environment. Imagine surviving a titanic merger only to be flung across the galaxy. The universe does not always believe in quiet recovery periods. Some mergers may occur in gas-rich environments, such as accretion disks around supermassive black holes, potentially producing light as well as gravitational waves. Others happen in cleaner emptiness, almost entirely dark except for the waves. Astronomers are eager to connect these possibilities because multi-messenger observations combining gravity and light reveal even more. Now let us scale upward. So far we have mostly discussed stellar mass black holes, but supermassive black holes at galactic centers can also merge when galaxies collide and eventually combine. These titanic binaries orbit slowly and emit lower frequency gravitational waves beyond current ground-based detector ranges. Future observatories such as LIGO aim to detect these deeper, slower cosmic notes from space. If stellar black hole mergers are chirps, supermassive mergers may be bass tones rolling across the cosmos. The universe contains genres. There is something philosophically striking here. For centuries we studied the universe mainly through light. Then we learned to study it through gravity's vibrations. Entire populations of invisible objects became accessible. It was as though nature opened another sense. How many truths wait behind senses we have not yet invented? Black hole collisions also remind us that emptiness can be active. Space may look dark and calm while hidden giants spiral together for eons. No visible spectacle announces them until subtle waves arrive. Calm appearances are unreliable narrators. That lesson applies widely. A quiet room may contain deep thought. A still ocean may hide strong currents. A dark region of sky may conceal two black holes preparing to merge after a billion-year courtship. And when they do, the event passes Earth as a whisper in instruments. There is comfort in that too. Not everything important arrives loudly. Now, if you're listening late at night, perhaps the room around you seems still. Maybe the day's pace has finally eased. Yet beyond the ceiling, beyond the clouds, beyond the nearest stars, somewhere in the universe, black holes may be spiraling together right now. No one nearby hears it. No one sees flames. But space itself is getting ready to ring. After black holes collide in fractions of a second and stars explode in brilliant flashes, it may seem natural to imagine that the universe always expresses violence quickly. We are used to associating drama with speed. A crash is sudden, an explosion is immediate. Lightning arrives in an instant. Even our own anxieties often prefer urgency, but the cosmos has another style entirely. Sometimes the largest acts of destruction happen so slowly that, to any single human observer, they would look almost peaceful. This brings us to galactic collisions. At first glance, the phrase sounds catastrophic in the way one might imagine two cities driving into each other, which would admittedly raise planning concerns. Yet galaxies are not solid objects. They are immense gravitational systems containing stars, gas, dust, dark matter, star clusters, and usually a central supermassive black hole. The distances between individual stars are enormous. Space inside a galaxy is mostly empty, so when galaxies collide, it is not usually star-smashing star in some glittering pileup. It is stranger than that. Galaxies pass through one another, distort one another, stir gas, reshape orbits, trigger waves of star formation, feed central black holes, and gradually transform into new structures over spans of hundreds of millions or billions of years. It is destruction in slow motion. To appreciate the scale, let us begin with what a galaxy is. Our own galaxy, the Milky Way, contains hundreds of billions of stars, vast clouds of gas and dust, spiral arms, globular clusters, dark matter extending far beyond visible edges, and at its centre the supermassive black hole Sagittarius A star. The Milky Way is roughly 100,000 light-years across. That means light, moving at about 300,000 kilometers per second, needs 100,000 years to cross it. Human schedules do not map well onto such dimensions. Nearby is the Andromeda Galaxy, another giant spiral galaxy, currently moving toward us. In about 4 to 5 billion years, the Milky Way and Andromeda are expected to begin a major merger. This is not cause for alarm tonight. You likely have other plans first. Still, it is a useful example because it shows that even galaxies do not remain politely separate forever. Gravity draws large structures together. Over immense spans, encounters become inevitable. Now imagine watching two spiral galaxies approach. At first, from a distance, they might look graceful, vast pinwheels of stars sliding nearer through darkness. But as they interact gravitationally, tidal forces begin to stretch them. Spiral arms distort. Streams of stars are pulled outward into long tails. Gas clouds are compressed. The neat shapes begin to loosen. If sped up into a time-lapse, it would look almost liquid. This is one of the surprising truths of cosmic structure. Systems made of stars can behave visually like fluids when viewed over long timescales. Individual stars mostly continue on their own orbits, but collectively the galaxy flows. When galaxies first pass through one another, they may continue onward, only to be pulled back again by gravity. Multiple passes can occur. Each encounter redistributes energy and angular momentum. Each pass deepens distortion. Eventually the two systems settle into one larger galaxy. Often the result is an elliptical galaxy rather than a neat spiral. Ordered disks are disrupted. Orbits become more randomized. The elegant spirals are replaced by a smoother, rounder stellar population. So yes, galaxies can lose their original identities. Even on cosmic scales, mergers change personalities. Now let us address a common question. If two galaxies collide, do stars crash into each other constantly? Surprisingly, no. Stars are tiny compared with the distances separating them. If the Sun were a marble, the nearest star might be another marble thousands of kilometers away on this scale. Direct star-star collisions during galaxy mergers are relatively rare. The real action happens through gravity and gas. Gravity changes trajectories. Gas clouds, unlike stars, can collide and compress. When cold gas is squeezed, it can collapse into new stars. This means galactic collisions often trigger starbursts. periods of intense star formation where many new stars are born in relatively short cosmic times. So destruction and creation arrive together once again. Two galaxies disturb each other, and in the turmoil new stars ignite. The universe repeatedly refuses to separate endings from beginnings. Now these starbursts can be dramatic. Massive young stars form quickly, shining brightly and living short, energetic lives. Supernova rates rise later as those stars die. Radiation increases. Winds from hot stars reshape nearby gas. The merged galaxy can become far more active than either parent was alone. And then there are the central black holes. If each galaxy hosts a supermassive black hole, the merger may eventually bring those giants together. Gas funneled inward during the galactic interaction can feed one or both black holes, producing active galactic nuclei or quasars. Later, the black holes themselves may form a binary and eventually merge, releasing gravitational waves. So one galactic collision can trigger many layers of violence. Distorted stellar orbits, gas compression, starbursts, supernovae, black hole feeding, future black hole merger, all spread across time. It is not one bang. It is a long campaign. Astronomers have observed many galaxies in different merger stages, giving us something like snapshots of a process too slow to watch directly from start to finish. The antennae galaxies are a famous example. Two galaxies are entangled, with long tidal tails stretching outward like antennae. They are rich in star-forming regions caused by the interaction. The Whirlpool galaxy shows another kind of gravitational encounter, where a smaller companion influences spiral structure. The NGC 7252 reveals what a later stage merger can look like. By studying many such systems, astronomers reconstruct the sequence. This is one of science's quieter triumphs. When events take longer than civilizations, we infer motion through many examples frozen at different moments. Now let us return to the future Milky Way Andromeda encounter, because people understandably ask what happens to Earth. The answer is reassuringly anticlimactic in personal terms. The solar system is unlikely to experience direct stellar collision. Space is too roomy. The Sun may end up on a different orbit around the merged galaxy. The night sky would become spectacular for long periods, with Andromeda swelling across the heavens, streams of stars, dust lanes and changing structure visible over millions of years. But by then, the Sun itself will be approaching later life stages, and Earth's long-term habitability has other concerns. Cosmic scheduling rarely revolves around one issue at a time. There is also the matter of dark matter. Galaxies are embedded in large halos of dark matter, invisible material inferred from gravitational effects. During mergers, these halos interact gravitationally and help govern dynamics. In some famous systems, such as the Bullet Cluster, observations of separated visible matter and gravitational mass distributions provided strong evidence for dark matter's existence. So even invisible components participate in galactic violence. The seen and unseen collide together. Now, why call galactic collisions violent if they happen so slowly? Because violence is not only about speed, it is about scale, force, transformation, and consequence. Entire stellar systems are reshaped. Gas reservoirs are reorganized. Star formation histories are altered. Central black holes are fed. Future evolution changes permanently. If a mountain slowly crumbled over centuries, it would still be destruction. If continents drift and close oceans over millions of years, we still call it tectonic upheaval. Duration softens experience, not significance. That idea may be useful beyond astronomy. Some major changes in life happen suddenly. Others occur so gradually that we notice only in retrospect. Habits shift, relationships evolve, priorities rearrange. Years later, we realize a merger happened somewhere inside our routines. Slow-motion transformation can be just as real as abrupt crisis. The universe demonstrates both. There is something oddly calming about galactic collisions for this reason. They are immense yet unhurried. Nothing panics, gravity does not rush. Structures adapt over ages. Even chaos proceeds with patience. Imagine if human beings adopted galaxy pacing for minor inconveniences. The printer is not working. Yes, we shall address this over the next 400 million years. Perhaps not practical, but emotionally elegant. Now, visually, galaxy mergers can be among the most beautiful objects in astronomy. Long tidal tails, glowing knots of star formation, warped disks, luminous cores. They resemble art because gravity naturally creates curves, arcs, spirals, and layered forms. Again, we find the familiar pattern. Processes that are mechanically harsh can appear aesthetically graceful from a distance. Storm systems from orbit, ocean waves from cliffs, galaxies colliding through telescopes. Beauty does not require gentleness, and yet, for all their grandeur, galactic collisions are common enough to be a normal part of cosmic evolution. Many large galaxies grew through repeated mergers. Our own Milky Way has absorbed smaller galaxies before and continues to do so. Streams of stars around it are evidence of past meals. Galaxies are not static islands. They are historical records of encounters. This means the universe we inhabit was shaped by mergers long before we looked up to notice. Structures we take for granted were assembled through repeated gravitational negotiations. Even calm-looking galaxies may carry scars. That too feels familiar. It may feel natural to imagine that the greatest cosmic violence belongs only to collisions. Two things meet. Forces escalate, structures break, matter is rearranged. Very dramatic, very understandable. But the universe has another specialty. Sometimes nothing needs to crash at all. Sometimes one object simply sits in the center of a galaxy, waits patiently, gathers matter, and becomes brighter than the galaxy itself. This brings us to quasars. The name sounds compact and tidy, which is slightly unfair because quasars are among the most outrageous sustained power sources ever discovered. A quasar is not a star despite early confusion. It is not a simple explosion. It is not one glowing object in the ordinary sense. A quasar is the brilliantly luminous region surrounding a supermassive black hole that is actively feeding. That sentence may sound straightforward, but it hides extraordinary consequences. Let us begin with discovery. In the mid-20th century, astronomers using radio telescopes detected mysterious sources of strong radio emission in the sky. Some of these sources appeared star-like in visible light, tiny points rather than obvious galaxies. They were called quasi-stellar radio sources, later shortened to quasars. The name remained, even after we learned they were not stars at all. When astronomers measured their spectra, the truth became startling. These objects were enormously distant, meaning they must also be immensely luminous to appear so bright from billions of light-years away. Some emitted more light than entire galaxies containing hundreds of billions of stars, and yet the source region was relatively compact. This was deeply puzzling. How could something galaxy-bright fit inside a region smaller than a galaxy by huge factors? The eventual answer involved supermassive black holes. At the center of many galaxies lies a black hole containing millions or billions of times the mass of the Sun. On quiet days, such a black hole may sit there with modest influence and little visible spectacle, much like an executive pretending not to monitor everything. But when gas, dust, stars, or disrupted matter fall inward in large quantities, the environment changes. Matter does not usually drop straight in. It spirals inward, forming an accretion disk around the black hole. Material in the disk orbits rapidly. Inner regions move faster than outer ones. Friction, compression, turbulence, and magnetic interactions heat the gas to extraordinary temperatures. That heating releases radiation, a lot of radiation. So much radiation that the central region can blaze across the electromagnetic spectrum. Radio, infrared, visible light, ultraviolet, X-rays, and beyond. Again, The black hole itself remains dark. The brightness comes from the material struggling nearby. There's a useful irony here. The darkest objects known can produce the brightest neighbourhoods known. Now let us talk about efficiency. Nuclear fusion, the process powering stars, is impressively effective. It converts a small fraction of mass into energy. Our Sun has used this mechanism reliably for billions of years. Accretion onto black holes can be even more efficient. As matter falls deep into a gravitational well, enormous energy becomes available before the material crosses the event horizon. Depending on spin and details of the disk, a significant fraction of the infalling mass energy can be radiated away. This means black hole feeding can outshine stars pound for pound. The universe occasionally rewards terrible table manners. Now imagine a galaxy full of stars, each shining steadily. Then imagine its central black hole entering an active feeding phase and producing enough luminosity to dominate the galaxy's total output. That is a quasar. From far away, the host galaxy may even be hard to see because the core is so bright. Like trying to notice a candle holder while someone has replaced the candle with a lighthouse. Some quasars are visible from tremendous distances, allowing us to study the early universe. Light from certain quasars began its journey when the cosmos was young. We observe them as they were billions of years ago. That means quasars are not only powerful, they are historical beacons. They tell us that supermassive black holes already existed early in cosmic history, which raises a natural question. How did they grow so large so quickly? This remains an active area of research. Perhaps early black hole seeds formed from massive first-generation stars. Perhaps giant gas clouds collapsed directly into black holes. Perhaps growth rates were extreme in dense early environments. Whatever the route, some black holes reached astonishing masses surprisingly early. The universe once again did not ease into things. Now, if we could safely observe a quasar from a respectful distance, what might we notice? First, the accretion disk would glow intensely. Inner regions would be hotter and emit higher energy radiation. Outer regions cooler, but still luminous. Matter would orbit at huge speeds, in some cases significant fractions of light speed. Second, jets may emerge. Many active black holes launch narrow jets from regions near their poles, likely involving magnetic fields and black hole spin. These jets can blast outward for thousands or even millions of light years, accelerating particles and interacting with galactic gas. So while the disk shines, the poles may fire. Subtlety is not always the universe's preference. Third, the surrounding galaxy may feel the consequences. Radiation pressure, winds, and jets from an active quasar can heat or expel gas. This may suppress future star formation by removing the raw material needed to make stars. In other words, a feeding black hole can help regulate the growth of its host galaxy. That is remarkable. An object smaller than the solar system's scale in active regions can influence a galaxy tens of thousands of light years wide. Small centers, large consequences. This principle appears in many systems. Now let us compare quasars with explosions like supernovae or gamma-ray bursts. A gamma-ray burst may be brighter for a brief instant. A supernova may dramatically unmake a star. But quasars can sustain tremendous output over long periods, millions of years in some cases. That matters. A flash is impressive. A furnace burning at absurd levels for eons is another kind of impressive. If a gamma-ray burst is a camera flash, a quasar is an industrial floodlight powered by gravity and questionable appetite. Both deserve respect. Now, one especially famous quasar-associated black hole is TON 618, containing tens of billions of solar masses by some estimates. Objects like this strain ordinary intuition. Their masses rival small galaxies. Their influence extends across vast regions. And yet they grew through the same basic principle. Gravity gathers matter. Simple rules, extreme outcomes. There is something elegant about that. You do not need complicated ingredients to make astonishing structures. Given enough time, mass, and physics, even straightforward laws can produce wonders. Now are quasars dangerous? Nearby, certainly they would be inhospitable. High radiation environments, powerful winds, energetic jets, and intense dynamics are not ideal for quiet gardening. But Earth is not near an active quasar. Our galactic centre is relatively subdued at present. This is appreciated. One of the great comforts of astronomy is that many terrifying things are very far away. Distance often converts danger into beauty. The same jet that would be catastrophic nearby becomes fascinating through a telescope. The same luminous core that would sterilize close environments becomes data at billions of light years. Perspective does practical work. There is another calming thought hidden in quasars. They are temporary. Even supermassive black holes cannot feed furiously forever. Fuel runs low. Gas is exhausted or blown away. The bright active phase fades. The galaxy settles. The quasar sleeps. Cosmic excess has limits. That idea may be useful in smaller human contexts too. Intense periods often feel endless while we're inside them. Stress, deadlines, uncertainty, noise. Yet many energetic phases are temporary. Systems consume available fuel and quiet down. Not everything stays bright and frantic forever. Astronomers classify quasars as part of a broader family called active galactic nuclei, or AGN. Depending on viewing angle, brightness, jet orientation, and obscuring material, we observe related phenomena under different names: Seyfert galaxies, blazars, radio galaxies, quasars. Sometimes the difference is not what the object is, but how we happen to be looking at it. That is another recurring lesson. Observation shapes interpretation. A jet pointed toward Earth may look like a blazar, exceptionally bright and variable. Viewed from another angle, the same system might seem different. Reality remains itself. Perspective changes labels. Now think of the night sky again. Some faint point in telescope images may represent a quasar whose light began travelling when Earth was young, or before Earth existed in its present form depending on the source. It crossed expanding space for billions of years. Then it entered our instruments and told us of a black hole feeding in the ancient dark. There is something wonderfully patient about that. The universe keeps records in light, and we, late arrivals with curious minds and occasional back pain, learn to read them. Quasars also help map the cosmos. Their brightness allows study of gas clouds between galaxies. As their light passes through intervening matter, absorption lines reveal composition and structure across vast distances. So these violent feeding episodes become tools for understanding everything in between. Again, destruction and knowledge arrive together. After discussing black holes that outshine galaxies and collisions that shake space-time, it may seem difficult for an ordinary-sized star to impress us any further. Then the universe produces a magnetar. A magnetar is, in one sense, a neutron star. That already places it among the densest and most extreme objects known. It is the collapsed core of a once massive star, compressed into a sphere only around 20 kilometers across, containing more mass than the Sun. It may spin rapidly. Its gravity is immense. Its matter exists under conditions far beyond anything comfortable. But a magnetar adds something extra, an almost absurd magnetic field. And when astronomers say strong, they do not mean keep credit cards at a distance. They mean magnetic fields so powerful they can distort atomic structures, affect matter from great distances, and release tremendous energy when stressed. Among stars that are not black holes, magnetars are excellent candidates for most dangerous. Let us begin with scale. Earth has a magnetic field generated by motions in its liquid outer core. It guides compasses, helps shield us from solar particles, and politely contributes to auroras. A refrigerator magnet also has a magnetic field, though it is less useful for planetary defense. The Sun has magnetic fields too, responsible for sunspots, flares, and coronal mass ejections. A typical neutron star already has a powerful magnetic field. A magnetar exceeds even that by huge factors. Its magnetic field can be around 1,000 times stronger than an ordinary neutron star's, and trillions of times stronger than Earth's. In some estimates, fields reach around 10 to the 14th to 10 to the 15th Gauss. Numbers at this level stop behaving like numbers and begin acting like warnings. If a magnetar were placed halfway between Earth and the Moon, its magnetic field could severely disrupt electronics. Much closer, it could do worse. Fortunately, none are scheduled for nearby relocation. Now, how does such a thing form? The leading idea is that some massive stars collapse in supernovae under conditions that leave behind rapidly spinning neutron stars with turbulent interiors. Combined with convection and rotation, a dynamo process can amplify magnetic fields to extraordinary levels during the newborn phase. The result is a neutron star whose magnetic field is not merely strong but dominant. That field stores enormous energy, and stored energy, as we have learned repeatedly, often seeks an exit. Magnetars are unstable in interesting ways. Their magnetic fields can twist and stress the crust of the neutron star. Remember, neutron star crusts are believed to be incredibly strong, yet magnetar fields are capable of cracking them. These ruptures are called starquakes. A starquake sounds like something invented for dramatic fiction, but it is a real astrophysical term for crustal adjustments in these objects. When the crust shifts and magnetic fields reconfigure, bursts of X-rays and gamma rays can be released. So yes, the star itself can crack under magnetic tension. This is one of the universe's more direct methods of expressing discomfort. Now, imagine an object only city-sized, denser than imagination prefers, whose magnetic field can break its own crust and launch high-energy radiation into space. That is a magnetar on a difficult day. Most known magnetars are detected through their bursts. They may appear as soft gamma repeaters or anomalous X-ray pulsars, names that reflect discovery history rather than a tidy classification system. Astronomy often names things in stages. That was strange. Still strange. Let us keep the label. One of the most famous magnetar events occurred in 2004 from SGR 1806-20. It released a giant flare so intense that it affected Earth's upper atmosphere despite being around 50,000 light-years away. Think about that distance. Light itself needed roughly 50,000 years to travel from the source to Earth. Human civilization changed many times over in that span. Yet when the flare arrived, instruments detected it strongly enough to notice atmospheric effects. That is an extraordinary amount of energy from an object only tens of kilometers wide. The initial flash lasted fractions of a second, followed by a fading tail modulated by the star's rotation. For a brief moment, this distant remnant became one of the brightest extrasolar events recorded in our sky. Again, we meet the familiar contrast, immense violence arriving quietly as a signal. Now let us talk about why magnetars are considered dangerous. If one were very close to Earth, the radiation from major flares could be harmful. High-energy photons can damage atmospheres, affect electronics, and stress biological systems. Thankfully, known magnetars are far away. Distance continues to be one of our best cosmic safety features. But danger is not only about proximity. Magnetars are dangerous conceptually because they show how far nature can push known physics without forming a black hole. Matter remains matter. The star still exists as a star-like remnant, yet conditions are so extreme that quantum electrodynamics becomes relevant in unusual ways. In ultra-strong magnetic fields, even empty space behaves differently. Vacuum polarization effects can occur, where the vacuum acts in ways altered by intense fields. This is where everyday intuition politely excuses itself. Atoms themselves may be distorted under sufficiently intense magnetic influence. Electron behavior changes. Ordinary chemistry is no longer a useful guide. A magnetar is a reminder that familiar rules often apply only within familiar ranges. Now, many magnetars also rotate. Some spin every few seconds, slower than many pulsars because strong magnetic braking can sap rotational energy over time. Their magnetic fields act like cosmic brakes, slowing the spin while powering emissions. So they may begin life spinning rapidly, then gradually settle into slower rhythms while remaining energetically active. There is something almost elegant about that. Born in violence, aging through resistance. Their lives are not calm, however. Magnetars can produce bursts unpredictably. Periods of relative quiet may be interrupted by renewed activity. Internal stresses build, fields evolve, crusts respond. Again, long preparation followed by sudden release. The universe repeats themes because the laws are consistent. Now compare magnetars with black holes. Black holes dominate through gravity. Magnetars dominate through magnetism. Black holes hide behind event horizons. Magnetars announce themselves with bursts. Black holes bend time dramatically. Magnetars bend matter and fields to startling extremes. Both are compact remnants of stellar death, yet their personalities differ considerably. If black holes are silent executives of gravity, magnetars are stressed engineers throwing sparks. Now compare them with supernovae. A supernova is a brief terminal explosion of a star. A magnetar may be born from that explosion and then continue producing violent outbursts for thousands of years. The ending creates a sequel. That is useful to remember when discussing cosmic violence. Some events are single finales, others leave unstable survivors. Magnetars also help explain mysterious phenomena. Some researchers have connected at least certain fast radio bursts, those brief intense radio flashes from distant galaxies, with magnetar activity. In 2020, a galactic magnetar called SGR 1935 + 2154 produced an event resembling fast radio bursts, strengthening the case that magnetars can generate at least some of them. So objects already known for extreme magnetic tantrums may also produce one of astronomy's newer mysteries. Overachievement continues. There is also a philosophical charm to magnetars. They are small by cosmic standards, tiny compared with galaxies, modest compared with giant stars, barely city-sized compared with the scale of solar systems, yet their influence can be felt across thousands of light years. Size and impact are not the same thing. That lesson appears often in nature and life. Small centers can hold immense power. A tiny seed becomes a forest. A small device in your pocket reorganizes modern behavior. A compact remnant star alters surrounding space with fields beyond reason. Never judge importance by diameter alone. Now, if you are listening late and beginning to feel pleasantly distant from the day's concerns, magnetars offer another comfort. Even the universe contains objects under enormous pressure, carrying internal stress, occasionally cracking, releasing energy, then continuing onward. Not ideal, perhaps, but relatable. The difference is that your own stress responses are unlikely to ionize atmospheres several star systems away. Probably. And thankfully, unlike magnetars, we have gentler tools available. Rest, quiet, perspective, hydration, perhaps a blanket, perhaps deciding tomorrow can handle some of tomorrow's problems. Magnetars do not seem to own blankets. This may explain much. Far from the gentle image many people carry of space as a quiet emptiness, there are places where matter is launched in narrow streams so powerful and so persistent that they can cross distances measured not in kilometers, not in planetary orbits, but in thousands or even millions of light years. These are cosmic jets. They're among the strangest and most impressive structures ever found in the universe. Long, focused beams of particles and energy shoot outward from some of the most extreme environments known, moving at speeds close to that of light. They emerge from regions near black holes, neutron stars and other compact objects, then punch through surrounding gas like lances of organized chaos. And what makes them especially remarkable is this. The engines that create them are often tiny compared with the colossal lengths those jets eventually reach. A compact central source can generate beams larger than galaxies. That mismatch of scale is classic universe behaviour. Small cause, enormous consequence. Let us begin with the most common misunderstanding. A jet is not simply something being blown out like steam from a kettle. It is not random spray. It is not matter escaping because a black hole has become overfull and emotionally overwhelmed. Cosmic jets are structured outflows. They are focused, accelerated, and guided by magnetic fields, rotation, and gravity. They arise when matter spirals inward toward a compact object, forming an accretion disk. As gas circles faster and faster, magnetic fields become twisted and amplified. Energy is transferred into narrow channels above and below the disk. Then the material is launched outward. So while some matter falls inward, some is expelled in opposite directions along the poles. The universe once again enjoys opposites occurring simultaneously. Black holes pull inward with extraordinary force, yet regions around them can hurl matter outward at extraordinary speed. This does not violate the black hole's reputation. The material in the jets generally comes from outside the event horizon, from the hot, magnetized environment surrounding it. The black hole remains a one-way boundary. The drama happens nearby, and dramatic it certainly is. Some jets move at relativistic speeds, meaning large fractions of the speed of light. At those velocities, special relativity matters. Brightness changes depending on viewing angle. Time appears differently in some processes. Particles gain enormous energies. If one jet points roughly toward Earth, the source can appear especially bright and variable. Such objects are called blazars because astronomy occasionally names terrifying phenomena with surprising cheerfulness. Now, where do we find these jets? One major home is the centre of active galaxies. There, supermassive black holes millions or billions of times the mass of the Sun feed on in falling gas. As matter spirals inward, some systems launch colossal jets extending far beyond the visible galaxy itself. A famous example is M87 star in the galaxy Messier 87. This black hole powers a jet thousands of light-years long, visible in many wavelengths. It is also the black hole whose shadow region was famously imaged by the Event Horizon Telescope collaboration. So one object gave us both a portrait and a spear. That feels efficient. Jets also occur on smaller scales. Stellar mass black holes in binary systems can feed from companion stars and launch miniature versions called micro-quasars. These systems are much smaller than active galactic nuclei, but the same general physics appears to operate. Scale changes, principles repeat. Neutron stars can produce jets too. Even some young forming stars, long before becoming anything especially dangerous, launch bipolar jets as they gather material from surrounding disks. Apparently, if matter spins and magnetic fields cooperate, jets become an appealing option. The universe has favourite engineering solutions. Now let us consider what a jet actually does once launched. It travels outward through surrounding gas, often remaining narrow over astonishing distances. That alone is difficult to achieve. On Earth, maintaining a clean beam through messy environments is challenging, yet cosmic jets can stay collimated across scales that mock ordinary intuition. As the jet ploughs through interstellar or intergalactic material, shock fronts form. Particles are accelerated to high energies. Lobes or hotspots can develop at the ends where the jet slams into surrounding medium. So a jet is not merely a beam, it is a sculptor. It carves cavities in gas, it heats environments, it redistributes energy across huge regions. In galaxies and clusters, jets can prevent gas from cooling too quickly, influencing future star formation. This means black holes can regulate their host systems not only by consuming matter, but by blasting energy outward through jets. A central object smaller than the solar system can affect structures millions of times larger. Again, small centres, large consequences. There is a lesson there that extends beyond astrophysics. Now, why call jets violent? because of the energies involved, the speeds involved, and the impact they have on surrounding matter. Gas struck by jets can be heated to millions of degrees. Particles can be accelerated to cosmic ray energies. Clouds can be compressed or disrupted. Large reservoirs of gas can be stirred and prevented from settling quietly into stars. Violence in the universe is often measured less by noise and more by rearrangement. Jets are excellent rearrangers, and still, from enough distance, they can look graceful. Images of radio galaxies often show elegant twin lobes stretching outward like wings. Optical and X-ray views reveal narrow luminous threads. Symmetry appears where force is immense. Beauty and brutality remain close companions in astronomy. Now imagine watching one in accelerated time. Near the centre, matter spirals inward in a glowing disk. Magnetic fields twist like taut cords. Then beams launch in opposite directions, punching through space. Knots of brighter material move along the jet, perhaps caused by changes in the engine or shocks in the flow. At the ends, giant lobes swell where energy piles up. It would resemble some impossible fountain built by gravity, and yet all of it follows physical laws we increasingly understand. That is another comforting pattern. Extreme does not mean chaotic in the useless sense. The universe can be wild and lawful at once. Now, there remains an important mystery. Exactly how jets are launched and collimated in detail is still an active field of research. Broad ideas are strong. Magnetic fields likely play central roles. Rotation of the accretion disk matters. Spin of the black hole may contribute through processes such as the Blanford-Znajek mechanism, where rotational energy is extracted electromagnetically. Even the names sound like they belong in a distinguished workshop. Scientists model jets with equations, simulations and observations across wavelengths. Radio telescopes trace large structures. X-rays reveal hot regions. Gamma rays expose extreme particle acceleration. Interferometry can resolve fine details near launching zones. We are studying beams from monsters with remarkable patience. Now let's talk about orientation, because perspective changes everything. If a jet points sideways relative to us, we may see extended structure clearly. If it points more directly toward us, relativistic effects can make it seem brighter and more variable. This is because emitted radiation is beamed in the direction of motion. So the same physical system can wear different labels depending on where we stand. The object stays itself. Our viewpoint changes the story. That is not only true in astronomy. There's also a quieter emotional comfort in jets. They are evidence that inward collapse does not always end inwardly. Matter falling toward a black hole might sound like pure loss. Yet some of that environment channels energy outward farther than almost anything else can carry it. Pressure becomes direction. Inflow creates outflow. Compression launches extension. Again, nature likes paradox. If life occasionally feels like that too, perhaps there is company in the cosmos. Times of pressure can produce motion. Constraint can create focus. Not every inward pull ends in disappearance. Some become beams. Now, are jets dangerous to nearby regions? Certainly. A sufficiently close and directly impacting relativistic jet from an active galactic nucleus would be bad news for local planetary atmospheres and biological ambitions. Radiation and energetic particles are not gentle companions. Fortunately, our neighbourhood is not currently dealing with one aimed at us from nearby. The Milky Way's central black hole is comparatively quiet. This is appreciated. The universe contains many alarming possibilities, yet distance and timing often behave kindly. One of the reasons jets fascinate astronomers so deeply is that they connect the very small to the very large. Physics near an event horizon influences gas across galactic scales. Magnetic processes near compact objects shape structures visible across millions of light years. The centre speaks, the outskirts respond. This relationship appears widely in nature. Tiny genes shape large organisms. Small tectonic shifts reshape continents. Microscopic chemistry alters climate over time. In cosmic jets, compact engines redraw giant environments. Now imagine the night sky again. Many of those faint points may host galaxies with central black holes. Some of those black holes may once have launched jets. Some may do so now. Their beams could be crossing emptiness for ages, interacting with gas, fading, reigniting, leaving signatures we detect long after the central conditions changed. The universe remembers activity through structure. That is useful to remember personally too. Actions often outlast moments. Energy leaves traces. Direction matters. Long before stars exploded, before galaxies collided, before black holes fed at the centres of cosmic cities, the universe itself passed through conditions so extreme that every violent event we have discussed so far would have seemed almost local by comparison. Because there was an era when the entire observable universe was the event, not a region within it, not one object among many, everything. When we speak about violence at the beginning of time, we should be careful with the language. The early universe was not violent because it was angry, unstable in a careless sense, or recklessly dramatic. It was violent because it was unimaginably hot, unimaginably dense, rapidly changing, and filled with energies beyond anything now found in ordinary cosmic environments. All of space was compressed into conditions so intense that matter, light, and forces behaved in ways very different from the calmer universe we know today. This is where scale reaches its highest setting. Let us begin gently. The Big Bang is often misunderstood as an explosion that happened in empty space, sending matter outward into a pre-existing void. That image is common, vivid, and not quite right. The Big Bang was not an explosion in space. It was an expansion of space itself. There was no central point from which galaxies were fired like cosmic confetti. Instead, space everywhere in the observable universe was once much hotter, denser, and closer packed, then began expanding and cooling. Every region participated. So if you ask where it happened, the answer is awkward but honest. Everywhere. That alone is strange enough to deserve a pause. Now imagine rewinding the current universe. Galaxies draw closer, temperatures rise, matter crowds together, radiation intensifies. Continue far enough back and you reach epochs where atoms cannot exist, where nuclei struggle, where particles collide constantly in a blazing plasma. Continue farther still, and even our best theories begin to lose confidence. Physics remains powerful, but not infinitely complete. That humility is worth appreciating. Still, we know a great deal about early stages after the first tiny fractions of a second. And what we know describes a cosmos operating under astonishing intensity. Within the first moments, temperatures were so high that familiar matter could not hold together. There were no atoms, no stars, no planets, no chemistry, no oceans, no listeners quietly settling into bed. There were only fundamental particles, radiation, and rapidly evolving conditions. It was not empty, it was crowded beyond reason. Particles collided constantly. Energies were immense. Space expanded furiously. The universe was a furnace without walls. Now, one of the most dramatic ideas in modern cosmology is cosmic inflation. According to leading models, a tiny fraction of a second after the beginning, the universe may have undergone an extraordinary burst of accelerated expansion. In a minuscule instant, space itself expanded by enormous factors. Regions once subatomic could become macroscopic. Tiny quantum fluctuations could be stretched to cosmic scales. This sounds abstract until one realizes that those tiny fluctuations may later become the seeds of galaxies and large-scale structure. So minute irregularities in a violently expanding infant universe eventually became clusters, stars, planets, and eventually beings asking what happened. That is a remarkable inheritance. Inflation, if correct, helps explain why the universe looks so uniform on large scales, and why geometry appears close to flat. It also suggests that structure began with fluctuations amplified during this early expansion. The quiet night sky may trace its ancestry to microscopic wrinkles. Now, after the universe expanded enough to cool somewhat, another important era arrived, the quark-gluon plasma phase. Under sufficiently high temperatures, quarks, which later become parts of protons and neutrons, were not confined neatly inside those particles. Instead, matter existed in a hot, dense soup of fundamental constituents. The phrase soup sounds comforting. This was not that kind of soup. Temperatures exceeded anything found naturally in modern everyday settings by absurd margins. Particle collisions happened constantly. Forces operated in high-energy regimes we recreate only briefly in accelerators such as the CERN. Eventually, as cooling continued, quarks became bound into protons and neutrons. This process mattered immensely. Stable building blocks were emerging. Later still, within the first few minutes, the universe entered primordial nucleosynthesis. Conditions allowed light nuclei to form, mainly hydrogen, helium, and traces of lithium. No stars were required yet. The whole universe itself briefly served as the nuclear environment. That means some of the hydrogen in water, in stars, in distant clouds, and in your own body traces directly back to those earliest minutes. Ancient does not begin to cover it. Then expansion continued. Temperatures dropped further. For hundreds of thousands of years, the universe remained a hot plasma of nuclei and electrons with light scattering constantly. Photons could not travel freely because they were repeatedly interacting with charged particles. The universe was opaque. No clear view across great distances. Then came recombination, around 380,000 years after the beginning. Electrons joined nuclei to form neutral atoms. Suddenly, light could travel much more freely. The universe became transparent. That ancient light still exists today, stretched by cosmic expansion into microwaves, known as the cosmic microwave background. It is one of the greatest discoveries in science. A faint afterglow from the early universe fills the sky in every direction, not visible to eyes, but measurable with instruments. A relic of hot beginnings still bathing us quietly. The past is not gone, it is cooled and everywhere. Now where is the violence in all this? Everywhere in the conditions. Temperatures of millions, billions, then trillions of degrees in earlier phases. Particle energies beyond ordinary stars. Rapid expansion of space. Matter and antimatter interactions. Constant collisions. Formation of the first structures from tiny fluctuations. No single supernova, black hole jet, or magnetar flare compares in scale because those are events within the universe. The early universe involved the state of the universe itself. That is a larger category entirely. There is also the mystery of baryogenesis, why matter exists in greater abundance than antimatter. In many models, the early universe should have produced both in nearly equal amounts. If perfectly balanced, they would largely annihilate, leaving a cosmos dominated by radiation. And yet matter remained. Some slight asymmetry favoured matter. That tiny imbalance made galaxies, stars, planets, and people possible. So one of the most consequential violent epochs also contained one of the gentlest differences, a slight preference. Huge outcomes can begin with small asymmetries. Again, a useful lesson. Now consider the first stars. After recombination, the universe entered a long dark age. No stars yet shone. Matter gradually gathered under gravity into denser regions. Eventually, the first stars ignited, likely massive, hot, and short-lived. These population 3 stars may have transformed the cosmos by producing heavier elements and rionizing surrounding gas. So even after the earliest furnace cooled, new violence emerged from gravity's patient work. Darkness gathered fuel, then stars began. The universe alternates between waiting and ignition. Now, one might reasonably ask, if the early universe was so chaotic, why does the cosmos now appear orderly? Because expansion cools systems. Density drops. Conditions change. Forces that once dominated become less overwhelming. Structures emerge. Galaxies form. Stars settle into long lifetimes. Planets cool. Chemistry becomes subtle enough for biology. Calm can grow from intensity. This happens in many systems. Molten rock becomes continents. Storm-tossed seas deposit quiet sediments. Busy childhoods become reflective adults. High-energy beginnings do not prevent later stability. Sometimes they enable it. There is another comforting thought hidden here. The universe did not begin finished. It developed. It cooled, organized, structured itself over time. Complexity emerged gradually. If your own life feels unfinished tonight, that places you in respectable company. Even the cosmos needed time. Now let us talk scale once more. A gamma-ray burst may last seconds. A supernova may blaze for weeks. A galactic merger may take eons. The early universe contains all these styles and more. Some transitions were incredibly rapid. Others unfolded over long stretches. It was not one moment of drama, but a sequence of changing eras. Beginnings are often processes, not instants. That is true cosmologically and personally. There are still unanswered questions. What exactly triggered inflation if it occurred? What happened before inflation, if before even applies meaningfully? What is dark matter, already influencing structure formation? What is dark energy, shaping later expansion? How do quantum gravity and relativity reconcile at earliest times? Our maps improve, but edges remain. That too is calming. Mystery survives even after great progress. One need not solve everything to understand something meaningful. Now imagine the night sky again. Every star you see formed because the universe cooled enough for atoms, then clouds, then gravity-driven collapse. Every galaxy traces amplified fluctuations from ancient conditions. Every heavy element from later stellar processes depends on earlier hydrogen and helium forged near the beginning. Everything visible tonight is downstream of those first violent eras, including you. You're not separate from cosmic history. You're one late expression of it, assembled after billions of years of cooling, structure, chemistry, and chance. That can make present worries feel smaller without making you smaller. You belong to a very old story. Not every violent event in the universe announces itself with light. Some do not blaze like supernovae. Some do not flash gamma rays across billions of light years. Some do not launch jets or crack stellar crusts or ring spacetime like struck metal. Instead, they happen partly in silence and partly in darkness, leaving clues only through gravity. This brings us to dark matter collisions, one of the strangest categories in all of astronomy. Because here, the battle involves something we cannot directly see. Dark matter is the name given to an unseen form of matter inferred from its gravitational effects. Galaxies rotate too quickly for visible matter alone to hold them together. Clusters of galaxies contain more gravity than stars and gas can explain. Light from distant objects bends around invisible mass through gravitational lensing. Again and again, observations suggest that much of the universe's matter is dark. Not dark because it is evil, hidden with intention, or wearing theatrical clothing. Dark because it does not emit, absorb, or reflect light in the ordinary ways we can easily detect. It interacts gravitationally, and perhaps weakly in other ways, but remains frustratingly elusive. So when we discuss dark matter collisions, we're often talking about collisions between galaxy clusters, the largest gravitationally bound structures in the universe, where dark matter plays a dominant role. These are not small encounters. A galaxy cluster can contain hundreds or thousands of galaxies, enormous clouds of hot gas, and vast halos of dark matter outweighing the visible material. When two such clusters meet, the scale becomes almost absurd. Entire systems hundreds of trillions of times the mass of the Sun pass through one another. This is violence written in very large handwriting. Now, unlike solid objects colliding, clusters are complicated mixtures. Galaxies themselves are relatively tiny compared with the space between them. So many individual galaxies pass by without direct collision. Hot gas clouds, however, do interact. They ram into one another, slow down, compress, heat, and emit strong X-rays. Dark matter, as best current evidence suggests, mostly passes through with much less interaction than the gas. That difference creates one of the most important cosmic laboratories ever found. The most famous example is the Bullet Cluster. The name is excellent. Scientists deserve occasional credit for choosing memorable labels. The Bullet Cluster consists of two galaxy clusters that have collided. In visible light, one sees galaxies. In X-rays, one sees hot gas slowed and shocked by the collision. But when astronomers mapped the total mass using gravitational lensing, they found most of the mass was not where most of the hot gas was. Instead, the dominant mass travelled with the galaxies, separated from the slowed gas. This was a landmark result. Why? Because if visible matter alone explained gravity, the mass should have followed the gas, which contains much of the ordinary matter. But the lensing map showed otherwise. Something massive and mostly collisionless had moved ahead. That something strongly supports the existence of dark matter, so a cluster collision became evidence for invisible mass. Sometimes the clearest proof of something hidden comes when systems crash. Now let us slow down and imagine what such a collision means. Two galaxy clusters approach over immense spans of time, drawn together by gravity. Their relative speeds may reach thousands of kilometers per second. Individual galaxies glide through mostly empty space. But the diffuse hot gas filling the clusters cannot ignore the encounter. Gas meets gas. Shock fronts form. Temperatures rise to tens of millions of degrees. The gas slows, piles up, and glows in X-rays. Meanwhile, dark matter halos appear to pass through more easily, continuing onward with the galaxies. It is like watching two crowds move through fog while the fog itself collides and stalls. Again, not a perfect analogy, but serviceable in the night hours. Now, why call this violent if so much simply passes through? Because scale and energy matter. Cluster collisions are among the most energetic events since the Big Bang. The kinetic energies involved are immense. Shockwaves span millions of light years. Gas is heated to extraordinary temperatures. Structures are rearranged on colossal scales. Nothing explodes in a cinematic instant. Everything transforms over time. That pattern should feel familiar by now. Some of the universe's largest upheavals are patient ones. The Bullet Cluster is not alone. Other merging clusters such as Max J 002 5.4-1222 and the Musket Ball Cluster have also helped test dark matter ideas. Each collision acts as a natural experiment. No laboratory on Earth could reproduce. We cannot smash galaxy clusters together on command. We must wait for the universe to do it and then take notes. Astronomy often involves elegant opportunism. Now, let us discuss gravitational lensing, because it is one of the key tools here. Mass bends space-time. Light travelling near massive objects follows curved paths. This can distort, magnify, or multiply images of more distant galaxies behind a cluster. By measuring these distortions statistically across many background galaxies, astronomers reconstruct the mass distribution of the foreground cluster. This lets us see invisible mass through its gravitational effects. Dark matter does not need to shine if it can bend light. There is something satisfying about that. Refusal to glow is inconvenient, but gravity still leaves fingerprints. Now, what exactly is dark matter made of? That remains unknown. Leading possibilities include new particles not yet directly detected, such as WIMPs, axions, or other candidates beyond the standard model of particle physics. Some alternatives attempt to modify gravity itself rather than invoke unseen matter, but the weight of multiple lines of evidence favours some form of dark matter. Still, its true identity remains one of the great unsolved problems in science, so cluster collisions do not only show us violence, they show us ignorance, honestly and productively. We know something real is there. We are still learning what it is. That is an admirable scientific position. Now consider how strange it is that most matter in the universe may be invisible to ordinary sight, and that we learned this partly because giant clusters crashed into each other. It is a reminder that calm appearances are incomplete. A starry sky looks like luminous matter dominates everything. Yet stars may be a minority component of cosmic mass. Vast invisible scaffolding shapes galaxies and clusters. The visible universe may be decoration on a hidden structure. That thought can feel unsettling or wonderful depending on the hour. Tonight, let us choose wonderful. Now imagine observing a cluster merger over millions of years in time-lapse. Galaxies stream through each other like swarms of fireflies. Hot gas clouds slam together, billow and shock. Invisible halos overlap and separate. Arcs of lensed background galaxies distort as mass moves. Eventually the systems settle into a new, larger cluster. It would look less like a crash between solid things, and more like weather in a gravitational ocean. Again, the universe prefers fluid elegance over blunt mechanics. There is another subtle point here. Dark matter collisions, as currently understood, may often be more like dark matter pass-throughs. If dark matter interacts weakly with itself, halos can cross with limited friction. That very property is informative. By measuring how separated components behave, scientists constrain how strongly dark matter particles might interact. So even the absence of dramatic sticking tells a story. Sometimes what does not happen is data. This applies beyond astrophysics more often than people realize. Now, these invisible battles also matter for cosmic history. Dark matter helped seed structure formation early in the universe. Ordinary matter later fell into those gravitational wells, forming galaxies and stars. Without dark matter, the large-scale universe might look very different. So when dark matter halos collide today, they are not just passing masses, they are ancient architects meeting again. There is something poetic there, though we promise not to become too poetic, so let us call it historically interesting instead. Now, if your own mind has been busy lately, cluster collisions offer perspective in a soothing form. Some changes are noisy and obvious, others are profound yet subtle, visible only through secondary effects. A person may look calm while carrying unseen forces. A system may seem stable while hidden structures govern outcomes. The universe contains much that matters but does not glow. That includes patience, memory, trust, quiet resilience, and whatever internal mechanism brought you here tonight to listen about invisible mass instead of doom scrolling. A respectable choice. There is also comfort in scientific humility. We have mapped genomes, landed probes, imaged black holes, detected gravitational waves, and yet much of cosmic matter remains unidentified. Mystery survives progress. That means uncertainty is not failure, it is frontier. Now, compared with supernovae, gamma-ray bursts or black hole mergers, cluster collisions may seem less flashy. They lack a single dramatic instant, but in total energy, scale, and consequence, they belong firmly among the grandest violent processes known. Entire clusters meet. Gas shocks across millions of light years. Invisible mass reveals itself. Galaxies are rerouted. Future structure changes. That is enough to earn a place on our list. While galaxy clusters collide across millions of light years and black holes merge with enough force to wrinkle space-time, there is another kind of violence passing through the universe in a much smaller package. It may be no larger than a single atomic nucleus. It may cross interstellar or intergalactic distances nearly at the speed of light. It may strike Earth's atmosphere carrying more energy than a professionally engineered particle accelerator can give to a proton. And most of the time, we never notice. These are cosmic rays. The name sounds like something visible, perhaps glowing beams sweeping through space like searchlights. In truth, cosmic rays are mostly not rays at all. They're charged particles, protons, atomic nuclei, and occasionally electrons or other particles accelerated to extraordinary speeds. The term remains from an earlier era of discovery, when their nature was not yet fully understood. Astronomy and physics have many such names. One learns to be forgiving. Now, cosmic rays come in many energies. Some are relatively modest by cosmic standards. Others are so energetic that they become legendary among physicists. And what makes them fascinating is this contrast. They are tiny, yet they carry immense motion and energy. A single particle can become a messenger from violent astrophysical environments far beyond Earth. Let us begin with discovery. In the early 20th century, scientists noticed that electroscopes, instruments sensitive to electric charge, would gradually discharge even when shielded from known local sources. Something invisible was ionizing the air. At first, many assumed the radiation came from Earth itself. Then Victor Hess took electroscopes aloft in balloon flights in 1912. He found that ionizing radiation increased with altitude. The source was coming from above. For this work, Hess later received a Nobel Prize. Sometimes science advances because someone agrees to take sensitive instruments into the sky in a basket. Now, where do cosmic rays come from? That depends on energy. Many lower energy cosmic rays originate from the Sun, especially during solar events. These are important for space weather and can affect astronauts, satellites, and technology. Higher energy cosmic rays likely come from supernova remnants, where shock waves from exploding stars accelerate particles through repeated interactions with magnetic turbulence. Think of particles bouncing back and forth across moving shock fronts, gaining energy each pass. The universe occasionally runs particles through a cosmic pinball machine. At even higher energies, likely sources include active galactic nuclei, relativistic jets, gamma-ray bursts, and other extreme environments. Some of the highest energy cosmic rays may have travelled from outside our galaxy, so a particle striking our atmosphere tonight might have begun its journey near a black hole billions of years ago. That is a rather committed travel itinerary. Now let us talk about speed. Many cosmic rays move extremely close to the speed of light. At such velocities, relativity becomes important. Their kinetic energies soar. Time and momentum no longer behave in purely everyday ways. When these particles hit Earth's atmosphere, they collide with nuclei high above the surface and produce cascades of secondary particles. One incoming cosmic ray can generate a shower spreading downward through the atmosphere. Muons, electrons, photons, and other particles rain through the air. Some pass through buildings, some pass through you. Do not be alarmed. This is normal. Right now, tiny particles produced by cosmic rays are likely moving through your body harmlessly. They do this constantly. Space has excellent reach. You are, in a calm and routine sense, participating in particle physics. Now, most cosmic rays are not dangerous in daily life because Earth's atmosphere and magnetic field provide strong protection. The atmosphere acts like a shield and absorber, taking the initial impact high above us. The magnetic field helps deflect many charged particles. Once again, our planet proves thoughtfully designed for comfortable surface living. Without those protections, life would face a harsher radiation environment. This matters especially for astronauts beyond Earth's shielding, where cosmic radiation becomes a significant health concern for long missions. So while cosmic rays are subtle at ground level, they're taken very seriously in space travel planning. Now, let us meet one of the most famous examples in physics, the so-called oh my god particle. Yes, that is the informal name. Science remains charmingly human under pressure. Detected in 1991, this ultra-high energy cosmic ray carried an energy around 3 × 10 to the 20 electron volts, vastly beyond what single particles in human accelerators then achieved. For one tiny particle, this was astonishing. its energy on everyday scales was still small because it was only one particle. But compared with other particles, it was extreme. That distinction matters. A mosquito and a truck can both move, but context changes interpretation. For a proton-like particle to carry that much energy means some astrophysical accelerator somewhere had access to extraordinary conditions. Finding the source of such particles remains difficult, because charged particles are deflected by magnetic fields during travel. They do not point neatly back to origin like photons often can. They arrive with stories scrambled. Still, their existence tells us powerful accelerators operate in the universe. Now, how do cosmic environments accelerate particles so effectively? One common mechanism is shock acceleration. In supernova remnants, expanding shock fronts move through gas and magnetic fields. Charged particles scatter across the shock repeatedly, gaining energy with each crossing. Another involves magnetic reconnection, where stressed magnetic field lines rearrange and release energy. Jets from black holes and neutron stars can also accelerate particles in turbulent flows. In essence, wherever there are strong magnetic fields, violent motion, shocks, and large energies, particles may be launched to remarkable speeds. The universe wastes very little opportunity. Now consider the irony. Some of the grandest violent events in existence reveal themselves not only through glowing remnants or gravitational waves, but through lone particles arriving quietly at Earth. No fanfare, no visible streak, just a detector registering a tiny visitor. This is one reason cosmic rays are so beautiful scientifically. They connect the very large to the very small. A supernova shell many light years wide can influence a nucleus smaller than an atom. A black hole jet spanning galaxies may accelerate particles that eventually strike a sensor in a laboratory. Scale collapses elegantly. Now, cosmic rays have practical effects too. They contribute to background radiation. They can cause bit flips in electronics, especially in aircraft or spacecraft systems. They influence atmospheric chemistry slightly. They are used in imaging techniques. MONs produced by cosmic rays can help scan pyramids, volcanoes and dense structures by measuring how many pass through. So ancient monuments and violent stars are linked by particle showers. That sentence alone justifies science. Now let's talk about rarity. Low-energy cosmic rays are common. Ultra-high-energy cosmic rays are rare. Detecting them requires vast observatories spread over large areas because the particles arrive infrequently. Facilities such as the Pierre Auger Observatory study these extreme events using surface detectors and fluorescence telescopes. Huge detector networks waiting patiently for tiny particles. Again, the universe enjoys contrast. Now, compared with supernovae or gamma-ray bursts, should cosmic rays count as violent events? Individually, a single particle is not a galaxy-smashing catastrophe. But collectively, cosmic rays are products of violent accelerators. They are evidence that somewhere matter was driven to extraordinary energies. They are fragments of cosmic violence packaged as messengers, and some individual particles carry energies so extreme that they become landmarks in physics. So yes, they belong here, though in a more subtle category. They are not the explosion. They are the shrapnel, the sparks, the postcards. There is also something emotionally useful in their story. Tiny things can carry great force. A small action can travel far. A brief word can echo. A compact idea can alter a life. The universe demonstrates this repeatedly. Not everything powerful is large. Sometimes power arrives in a nearly invisible form. Now, if you are listening while resting, perhaps it is comforting to know that countless cosmic processes are underway without demanding your attention. Particles cross the sky, stars fuse, galaxies turn, detectors quietly count arrivals. You do not need to manage any of it tonight. The atmosphere is doing its job. Gravity remains consistent. Most particles will mind their own business. That is enough. There is another humbling thought here as well. human technology builds giant machines to accelerate particles and probe nature. Yet the cosmos has been running far larger accelerators for billions of years using shock waves, magnetic fields and relativistic jets. We are not inventing the game, we are learning from an older player. Many of the violent events we've explored so far come with a built-in comfort feature. They are far away. A black hole merger may release astonishing energy, but if it happens a billion light-years distant, that energy reaches us spread across vastness, diluted by distance, noticed mainly through delicate instruments. A supernova in another galaxy may look beautiful through telescopes while posing no threat at all. Even gamma-ray bursts among the brightest blasts known are usually remote historical signals crossing space with no personal appointment scheduled. Distance, in astronomy, is often kindness. So it is natural to ask a more personal question. Could any of these violent cosmic phenomena actually affect us? Could a supernova, gamma-ray burst, solar event or other process matter directly for life on Earth? The honest answer is yes, in principle. The calmer answer is that serious impacts from the most extreme cosmic events are rare, often very rare, and most known dangers are not immediate concerns. That balance matters. We do not need false reassurance, and we do not need dramatic panic. We need proportion. So let us move carefully through the possibilities. We begin with the most familiar star in the sky, the Sun. Compared with quasars, magnetars, or colliding black holes, the Sun seems almost modest. It is an ordinary main sequence star, yet because it is close, it is by far the most influential cosmic object in our daily lives. Nearness beats extravagance. The Sun can produce solar flares and coronal mass ejections, eruptions of energy and charged particles driven by magnetic activity. Strong solar storms can disturb Earth's magnetosphere, generate auroras, disrupt radio communication, damage satellites, and stress power grids. This is not hypothetical. The Carrington event caused telegraph disruptions and spectacular auroras. If a similar event occurred today, modern technological systems could face significant challenges. So the most likely cosmic event to affect daily civilization is not an exotic black hole drama. It is weather from our own star. That feels almost sensible. Now let us widen outward to supernovae. Could an exploding star affect Earth? Yes, if it happens sufficiently close. A nearby supernova might expose Earth to increased cosmic rays and high-energy radiation, potentially altering atmospheric chemistry or damaging the ozone layer. Exact thresholds depend on the type of explosion and conditions, but estimates often place concern within tens of light years, perhaps somewhat more depending on scenario. That sounds alarming until we add context. There are no known stars expected to explode soon at dangerously close distances. Many candidate supernova progenitors are far enough away that they would be visually spectacular rather than biologically troublesome. Take Betelgeuse. It may explode someday, though someday could mean tomorrow in cosmic terms or 100,000 years from now. It is far enough away that it would likely create a brilliant sky display rather than a planetary crisis. Astronomy frequently pairs drama with patience. Now, gamma-ray bursts. These often inspire concern because they are extremely energetic and directional. If a sufficiently close gamma-ray burst were aimed directly at Earth, it could damage the atmosphere, particularly ozone, increasing harmful ultraviolet exposure and triggering environmental stress. That possibility is one reason gamma-ray bursts receive attention in extinction discussions. However, several comforts arrive immediately. They are rare nearby. Their jets are narrow. The universe is large. No known local system currently presents an obvious imminent threat of this kind. So yes, in principle, dangerous. In practice, not something to lose sleep over tonight. And since this is science for sleep, that distinction is especially useful. Now consider asteroid and comet impacts. Strictly speaking, these are not the same category as supernovae or black hole mergers, but they are cosmic events that can directly affect Earth, and unlike many distant astrophysical extremes, they have happened repeatedly in geological history. The Cretaceous-Paleogene extinction event is the most famous example, associated with the impact that contributed to the end of non-avian dinosaurs. Here, proximity matters again. A modest asteroid nearby can matter more to Earth than a quasar billions of light-years away. Scale without distance can outweigh grandeur with distance. Fortunately, modern surveys track many near-Earth objects, and planetary defense efforts continue improving. This is one of the few cosmic hazards humanity can potentially mitigate with planning. It is reassuring when a threat category comes with engineering options. Now let us return to cosmic rays. High-energy particles constantly reach Earth, but our atmosphere shields us effectively. At the surface, ordinary exposure is low and part of natural background radiation. Airline crews and astronauts receive more due to altitude or reduced shielding. Very large increases in cosmic ray flux from nearby astrophysical events could matter, but ordinary ongoing cosmic ray presence is a normal part of living on a planet under a sky. You have already survived many particle arrivals with style. Now, black holes. Popular culture often worries about black holes wandering in and swallowing Earth unexpectedly, usually with poor timing. This is not a realistic near-term concern. There are no known black holes on trajectories threatening the solar system. Space is enormous. Encounters of that kind are extraordinarily unlikely. If a stellar mass black hole passed nearby, gravitational effects would be noticeable long before dramatic swallowing fantasies became relevant. Black holes are dangerous mainly when one chooses to go near them. We do not. This arrangement works well. What about the supermassive black hole at the centre of our galaxy, Sagittarius A star? It is about 26,000 light-years away and currently relatively quiet. It exerts gravitational influence mainly in the galactic centre region, not as some immediate threat to Earth. Again, distance is kindness. Now let us consider magnetic events from stars. Some stars flare far more violently than the Sun, especially certain red dwarfs. If Earth orbited one of those active stars at habitable zone distances, life might face difficult radiation environments. This is highly relevant for exoplanet habitability studies. But we orbit the Sun, not a flare-prone red dwarf. One occasionally forgets how fortunate certain local conditions are. Stable star, protective magnetic field, atmosphere, liquid water, reasonable orbital distance, no nearby quasar pointed at us. Quite a strong package. Now, beyond physical danger, cosmic events affect us intellectually and emotionally all the time. A total eclipse changes human mood. A bright comet inspires art. A meteor shower gathers strangers under dark skies. A supernova discovery changes textbooks. Gravitational wave detections expand our senses, so even when distant events cannot harm us, they can still matter deeply. Impact is not always destructive. Sometimes it is perspective. Now let us talk probability, because human minds often struggle with rare risks. We may ignore common manageable dangers while worrying intensely about spectacular unlikely ones. It is a very human habit. Driving distracted to buy snacks while fearing gamma-ray bursts is statistically creative. The universe does contain hazards, but everyday life usually contains more immediate ones. Stress, sleep deprivation, poor diet, loneliness, neglected maintenance, sending emails while tired. These are less glamorous than magnetars, yet far more likely to affect tomorrow morning. Perspective should calm, not mock. Real concerns matter, but understanding scale helps distribute attention wisely. Now, could future humanity reduce some cosmic risks? Yes. Better space weather forecasting can protect power grids and satellites. Asteroid detection and deflection technologies can reduce impact risk. Space habitats may someday spread risk across multiple worlds. Advanced astronomy helps us understand stellar neighborhoods and long-term threats. Knowledge is preventive comfort. We cannot stop a distant supernova. We can prepare for solar storms. We can track rocks. We can improve resilience. That is already meaningful. There is also another useful thought hidden here. The universe is not targeting us. Events happen according to physics, not personal narrative. A solar flare is not commentary on your week. A cloudy meteor shower is not cosmic sarcasm. The stars are not evaluating your progress. This may sound obvious, yet people often carry burdens as if everything reflects them. Most things do not, certainly not quasars. Now imagine Earth from far away. A small world with oceans, weather, thin atmosphere, one moon circling a medium star in an outer arm of a galaxy. Around it, the cosmos hosts collisions, explosions, jets, and ancient radiation. Yet here, life developed, music was invented, tea was prepared, and someone chose to listen to a soothing discussion of astrophysical danger. That is a lovely improbability. We are not outside the violent universe. We are one calm pocket within it. And calm pockets matter. There is another lesson here too. Safety is often local rather than universal. The broader cosmos can be intense while your room is quiet. Markets may fluctuate while a tree outside remains still. History can be noisy while one evening remains gentle. You do not need the whole universe calm in order to rest. You only need enough calm where you are. That may be the most practical astronomy lesson of all tonight. Why a galaxy collision can seem beautiful, while a broken glass at home feels urgent. Stand near a breaking glass, and your body reacts immediately. There is sound, motion, sharp edges, clean up, perhaps a brief and colourful vocabulary response. If a storm rattles windows, if thunder cracks overhead, if a car brakes suddenly outside, attention narrows, muscles tense. The nervous system becomes interested at once. Human beings are built to respond to nearby force. Now compare that with hearing that two black holes merged 1 billion light-years away. Intellectually, you may understand that the event released astonishing energy. Spacetime rippled. Mass became gravitational waves. Entire stars elsewhere may have lived and died between the moment it happened and the moment we detected it. Yet emotionally, the reaction is often calm curiosity. Perhaps even comfort. Why? Why does violence in space feel so different from violence close to home? The answer begins with scale. Human minds evolved to care intensely about local consequences. A falling branch matters more to survival than a distant volcano on another continent. A predator nearby matters more than tectonic processes across an ocean. The nervous system prioritizes immediacy, proximity, and relevance. This is sensible design. If our ancestors froze in awe every time a cloud looked interesting while ignoring the tiger 10 meters away, history would be shorter. So when cosmic violence reaches us only as information, not threat, our fear systems often remain quiet. We are free to engage curiosity instead. Distance changes meaning. A supernova in a distant galaxy is not an emergency. It is a story written in light. A quasar is not shouting at us. It is data crossing billions of years. A galaxy collision is not a crash beside the road. It is a slow transformation far beyond personal consequence. The same forces that would terrify nearby can fascinate from afar. This pattern is not unique to astronomy. People watch thunderstorms from porches more happily than from open fields. Ocean waves are soothing on shore, less soothing in a small leaking boat. Fire in a fireplace feels cozy. Fire in curtains does not. Context determines emotional tone. Now let us talk about time. Many violent cosmic events are fast in physical terms, but others unfold over spans too large for ordinary intuition. Galactic mergers take hundreds of millions of years. Stellar evolution takes millions to billions. Even sudden bursts often come after immense preparation. Because we do not experience these timelines directly, they feel less urgent. Urgency belongs to clocks we can feel. A deadline tomorrow activates the mind more than a star expected to explode in 80,000 years. The nervous system is many things, but it is not a specialist in geological or cosmological scheduling. This can be frustrating when planning retirement, but excellent for sleep. Now there is also silence. Space does not carry sound the way air does. The most violent events in the universe often happen without roars reaching us. We receive photons, particles, or gravitational signals, not thunder. Sound strongly influences emotional response. Sudden loud noises command attention. Silence softens perception. If every supernova arrived with a synchronized boom overhead, astronomy would feel very different. Fortunately, vacuum remains committed to acoustical restraint. Then there is beauty. Many violent cosmic processes create forms we experience as beautiful. Supernova remnants glow in delicate filaments. Jets trace elegant lines. Spiral galaxies distort into sweeping arcs during mergers. Nebulae bloom from stellar death. Beauty complicates threat. When danger is absent and aesthetics are present, wonder often replaces fear. This is why people frame images of black holes rather than filing complaints against them. Now let us examine numbers, because scale also breaks intuition. Suppose I tell you a gamma-ray burst released more energy in seconds than the sun will emit over billions of years. The statement is true in broad terms for some events, yet the mind struggles to picture it. When numbers become too large, emotional response often flattens. $100 feels different from 1,000. 1,000 feels different from 10,000. But 1 trillion and 1 quadrillion may both simply feel like very many. Likewise, cosmic scales become abstract. Without lived reference points, awe replaces practical alarm. This abstraction can actually soothe us. Vastness places personal worries into perspective without denying them. Your unfinished laundry still exists. It just does not compete numerically with quasars. Now, there is another reason cosmic violence feels different. Lack of intent. Human violence disturbs us deeply because it often includes suffering, agency, cruelty, or preventable harm. These dimensions matter morally and emotionally. A war is not upsetting merely because energy is released. It is upsetting because conscious beings are harmed. The universe's violence has no malice. Stars collapse because fuel runs out. Black holes merge because gravity governs motion. Galaxies collide because mass curves paths. There is no hatred in a supernova, no resentment in a magnetar flare, no personal commentary in a cosmic ray. This absence of intent changes how we receive it. Natural force may still be dangerous, but it does not carry the same emotional weight as cruelty. That distinction is important and humane. Now let us bring this closer. Sometimes people feel guilty for finding cosmic disasters beautiful or relaxing to think about. There is no need. You are not admiring suffering. You are admiring scale, lawfulness, structure, and the mind's ability to comprehend remote extremes safely. A tidal disruption event can be scientifically fascinating without anyone needing counselling afterward, because no conscious star filed objections, as far as we know. Now there is also the role of perspective itself. When we contemplate large systems, many smaller concerns temporarily loosen. Bills, awkward conversations, inboxes, delays, and minor frustrations can shrink in apparent size when placed beside galaxies. This does not make them unreal. It simply restores proportion. Perspective is not dismissal. It is resizing. Many people seek the night sky for exactly this reason. Looking upward can reduce self-centered pressure. Not because the self is worthless, but because it is not the whole frame. A larger frame can be merciful. Now imagine two scenarios. In the first, a glass falls from a kitchen counter. Immediate sound, sharp pieces, mess, possible barefoot consequences. In the second, astronomers announce a black hole merger 2.4 billion light-years away. One creates adrenaline. The other creates headlines and perhaps a thoughtful podcast. This is rational. The kitchen floor has jurisdiction. Now, there is something else worth noticing. Cosmic violence often creates future calm. Supernovae forge and distribute heavy elements needed for planets and life. Galaxy interactions can trigger star formation. Black hole feedback may regulate galactic gas. Early universe extremes enabled later chemistry and structure. Destruction and creation repeatedly arrive together. So when we look at violent space events, we're often looking at steps in larger generative processes. That softens them conceptually. Nature can be rough locally while constructive globally. Again, many systems work this way. Forest fires can renew ecosystems. Volcanism creates land. Muscle strain strengthens tissue when managed properly. Short-term disruption can serve long-term form. The universe scales this principle dramatically. Now let us speak quietly about personal life. Many people carry a sense that every immediate problem is absolute. A tense message feels enormous. An awkward mistake replays loudly. Waiting for uncertain news stretches time. This is understandable. The nervous system weights local events heavily. But cosmic perspective offers a counterbalance, not to erase pain or stress, but to remind you that feelings of scale are adjustable. A difficult day can be real and still small in a larger frame. Both statements can coexist. That is emotionally useful. Now imagine the Earth from orbit, then from beyond the Moon, then from the edge of the solar system, then as one pale point among stars. From those distances, many conflicts vanish visually. Borders disappear. Traffic does not show up. No one can see your to-do list. Reality remains, but framing changes. The same is true mentally. A wider frame can reduce unnecessary pressure. This may be one reason space documentaries pair so well with rest. They borrow grandeur to quiet urgency. Now, of course, we should not romanticize all natural violence. Nearby earthquakes, storms, impacts, or radiation events are serious. Scale alone does not make danger pleasant, but distant cosmic events are mostly encountered as knowledge, and knowledge can be calming when it enlarges perspective. There is also humility in realizing that our categories are local. We call events violent because they exceed ordinary balance relative to our expectations. The universe itself does not label them. To a star, collapse is consequence. To gravity, merger is geometry. To particles, acceleration is motion. Meaning belongs partly to observers. Tonight, you are the observer. And from here, in a quiet room, under blankets perhaps, with the day gradually loosening its grip, violence in space can feel less like threat and more like grandeur at a safe distance. That is a fortunate arrangement. If the universe contains so much chaos, why does it so often produce order afterward? Why do explosions lead to planets, collisions to stars, and upheaval to possibility? Order can be deceptive. A forest looks stable until you learn it depends on storms, decay, insects, competition, fire, and constant cycles of death and regrowth. A coastline seems permanent until tides, erosion, and shifting weather quietly redraw it year after year. Even the human body, which feels like a single continuous thing, is built from cells constantly replaced, repaired, recycled, and removed. Stability often rests on motion. The universe follows the same pattern, only at grander scales. After spending so much time with explosions, collisions, black holes, magnetars, and violent beginnings, it is natural to wonder whether all this chaos is merely destructive. Why so much upheaval? Why not a calmer cosmos filled with tidy stars behaving responsibly forever? The answer, as far as science can tell, is that much of what we value in the universe exists because disorder, instability, and energetic change were allowed to happen. Chaos, in many forms, is productive. Now, we should define terms carefully. Chaos here does not mean meaningless randomness or senseless wreckage. It means dynamic change, instability, competition between forces, and periods where systems reorganize dramatically. The universe needs those transitions. Without them, it would be far simpler and almost certainly far less interesting. Let us begin with stars. Stars form when large clouds of gas and dust fail to remain evenly spread out. Gravity amplifies tiny irregularities. Denser regions attract more material, becoming denser still. Eventually parts of the cloud collapse enough to ignite fusion. No irregularity, no collapse. No collapse, no star. So one of the most peaceful sights in the night sky begins with imbalance. A perfectly smooth universe would be a dark and boring place. This principle reaches back to the earliest cosmos. Tiny fluctuations in matter density after the Big Bang became seeds for galaxies and clusters. If the young universe had been perfectly uniform, gravity would have had little structure to work with. Matter would remain too evenly distributed. No galaxies, no stars, no planets, no listeners. Small unevenness made everything else possible. That is worth remembering whenever imperfections seem purely negative. Now consider supernovae. When massive stars die, they explode violently, scattering heavy elements into surrounding space. Those elements include carbon, oxygen, silicon, iron, calcium, and many others required for rocky planets, oceans, atmospheres, and biology. Without stellar death, much of the periodic table would remain locked inside stars or never form in abundance. So planetary surfaces, metal tools, mountains, blood chemistry, bones, and electronics all owe debts to ancient catastrophes. The universe uses endings as distribution systems. That may sound harsh, but it is effective. Now let us turn to galactic collisions. At first glance, two galaxies merging seems like needless roughness. Elegant spirals distorted, gas clouds shocked, orbits scrambled. Yet these mergers can trigger starbursts, periods of intense star formation. Gas compressed during interactions collapses into many new stars. Central black holes may grow. Larger galaxies are assembled from smaller ancestors. The modern universe was built partly through mergers. Cosmic cities expanded through repeated redevelopment. Again, disruption creates form. Black holes themselves offer another example. Their jets and energetic feedback can prevent galaxies from forming stars too quickly or too long. By heating or expelling gas, they help regulate growth. That sounds strange. One of the darkest and most intimidating objects known can contribute to long-term balance. But many systems require brakes as much as accelerators. Too much star formation too quickly could exhaust gas reservoirs. Feedback processes help shape sustainable histories. Even monsters can perform civic duties. Now think smaller. Planetary systems form from disks of gas and dust around young stars. Within those disks, particles collide, stick, shatter, regrow, migrate, and compete gravitationally. Worlds emerge through countless interactions, many of them messy. Early solar systems are not quiet clockwork displays. They are construction zones. Asteroids collide. Embryonic planets scatter one another. Orbits shift. Some worlds are lost. Others grow by accretion. Moons may form from impacts. Our own moon likely owes its existence to a giant collision early in Earth's history. So the tides, eclipses, and familiar companion in our night sky may trace back to planetary violence. Gentle moonlight, rough origin. That pattern repeats constantly. Now, let us consider life. Biological evolution depends on variation, competition, environmental change, extinction, and adaptation. Stable conditions can support life, but changing conditions often drive diversification and innovation. Mass extinctions are tragic in one frame and transformative in another. They erase many lineages, yet open ecological opportunities for survivors and future forms. The extinction that ended non-avian dinosaurs helped create a world where mammals diversified dramatically. No impact, no human path in quite the same way. This does not make catastrophe good in a moral sense. Nature is not moral theatre. it means consequences are layered. Loss and possibility often arrive together. Now there is a mathematical truth here too. Complex systems frequently need fluctuations. Perfect equilibrium can be sterile. Too much rigidity prevents adaptation. Too much disorder prevents persistence. Productive systems often live between those extremes, not frozen, not shattered, responsive. The universe seems fond of that middle ground. Stars balance gravity and pressure. Galaxies balance inflow and feedback. Planets balance climate forces. Ecosystems balance competition and cooperation. Human lives often seek similar ranges. Now, if you are listening while carrying some internal disorder of your own, stress, uncertainty, change, unfinished plans, it may help to remember that disruption is not automatically failure. Many worthwhile structures pass through unstable phases. Learning feels clumsy before it feels natural. Healing can feel messy before it feels whole. Reorganization often looks like confusion from the inside. The universe has extensive experience with this. Clouds collapse before stars shine. Stars explode before planets inherit their elements. Galaxies collide before new structures settle. There is another useful thought hidden here. Calm is often an outcome, not a starting condition. We sometimes imagine peace as something that should exist naturally unless disturbed. But many peaceful states are maintained through ongoing processes. A garden is calm because it is tended. A healthy body is stable because systems constantly regulate. A star shines steadily because fusion and gravity oppose each other continuously. Your own restful evening may require boundaries, routines, quiet choices, perhaps turning off devices that mistake agitation for importance. Calm can be built. That makes it more accessible, not less. Now, one might ask whether the universe needs chaos in any conscious sense. No, the universe does not hold preferences in that human way. It does not submit planning memos requesting occasional upheaval. The phrase is shorthand for this. Given the laws of physics, dynamic change is deeply involved in producing complexity. Without gradients, tensions, imbalances, collisions, flows, and feedback loops, many structures would never arise. Energy moving from concentrated states to dispersed states powers processes everywhere. Temperature differences drive weather. Pressure differences drive winds. Chemical differences drive metabolism. Gravitational differences drive collapse and orbit. Stored energy seeks pathways. Change follows. Now let us revisit some of our earlier cosmic characters. Gamma ray bursts, violent, brief, extreme. They may accompany stellar collapse or neutron star mergers, both tied to element production and remnant formation. Magnetars, unstable remnants, whose bizarre physics teaches us about matter and fields under extremes. Cosmic rays, particles accelerated by shocks and jets, carrying information across space. Dark matter collisions, giant structures whose mergers reveal hidden architecture. Even events that seem purely destructive often become sources of knowledge, matter redistribution, or future structure. Chaos creates data, too. That may be the most human benefit of all. Now imagine a universe with none of this. No stellar deaths, no mergers, no fluctuations, no instability, no recycling. Perhaps a thin uniform fog of particles expanding quietly forever, neat, simple, uninhabited. The lively cosmos comes with costs, but it also comes with stars, chemistry, weather, continents, ecosystems, and consciousness capable of noticing any of it. That is quite a return on turbulence. There is something deeply comforting in this for many people. We often resist change because it feels like loss of control, yet some of the best structures in existence were shaped by transitions no part of them could have predicted in advance. A gas cloud does not know it is becoming a star. A young planet does not know oceans are coming. An ecosystem after fire does not know what regrowth will look like. You may not know what current changes are preparing either. That uncertainty can be frightening, yes, it can also be fertile. Now, this does not mean every hardship is secretly wonderful or every disruption beneficial. Some losses are simply losses. Some damage should be prevented. Compassion matters. Repair matters. But it does mean that change itself should not automatically be mistaken for ruin. Nature uses change constantly. So perhaps tonight, if your own thoughts feel unsettled, you might borrow a gentler interpretation. Movement does not always mean collapse. Disorder does not always mean ending. Some forms of chaos are just systems searching for a new balance. The universe has spent billions of years doing exactly that. Somewhere above you right now, the universe is still in motion. Stars are burning through their fuel in steady silence. Black holes are feeding in hidden galactic cores. Two compact remnants may be spiraling together toward a merger that will not happen for another million years, or perhaps in the next hour. A particle accelerated near some ancient shockwave may be crossing empty space on a journey longer than human history. Galaxies continue drifting, rotating, gathering, separating, meeting again. Nothing has paused, and yet, here with you now, there can still be stillness. That is one of the loveliest truths we have found tonight. The universe does not need to become calm everywhere, for calm to exist somewhere. It does not need to silence every jet, every flare, every collision, every distant burst of radiation. It only needs this room, this moment, this breath, this small corner of time where you are resting. That is enough. We have travelled through extraordinary places together. We visited stars that end in explosions bright enough to rival galaxies. We watched neutron stars collide and create heavy elements. We passed by black holes that bend time and swallow light, then listened as some of them merged and sent waves across space itself. We stood back while galaxies crossed through one another over ages. We looked toward quasars blazing from hungry galactic centres. We met magnetars with fields so intense they can crack their own crusts. We followed cosmic rays, tiny particles carrying stories from violent engines far away. And then we went farther still, back to the early universe, where heat and density filled everything. Back to the first imbalance, the first structures, the first conditions from which all later stars and planets would emerge. It is a great deal to hold, so there is no need to hold it tightly. You do not need to memorize numbers tonight. You do not need to compare luminosities or recall merger rates or explain nucleosynthesis before breakfast. You only need the feeling of it, the sense that reality is larger than the day you had, the sense that many things can be active at once while peace remains possible, the sense that chaos and order are not enemies so much as partners taking turns. That perspective can be restful. Human life often feels close up. Bills arrive close up. Conversations happen close up. Regrets repeat close up. Tomorrow's tasks stand very near the face of the mind, requesting attention with unusual confidence. But astronomy quietly pulls the camera back. From farther away, many urgent things become smaller. Not meaningless, not silly, just smaller. A difficult email still exists, but it now exists in a universe containing quasars. Laundry still waits, but it waits in a galaxy 100,000 light-years wide. An awkward moment from last Tuesday remains historically real, yet it competes poorly with neutron star mergers for scale. This does not erase ordinary life. It softens its edges. There is mercy in scale. Now consider another lesson from the night's journey. Many of the most violent events we explored were also creative ones. Supernovae made elements needed for planets and bodies. Mergers triggered new stars. Ancient fluctuations became galaxies. Pressure produced structure. Endings redistributed possibility. If your own life contains unsettled parts, unfinished parts, parts under pressure, perhaps that lesson may travel with you a while. Not every period of instability is a collapse. Sometimes it is formation from the inside. Sometimes the shape is changing before the purpose becomes visible. Sometimes systems must rearrange before they can rest again. The universe has done this repeatedly for billions of years. You're allowed to do it on a smaller schedule. There is also comfort in knowing how little of cosmic violence concerns us directly tonight. No nearby gamma-ray burst is requesting your attention. No black hole is circling the house. No magnetar has added your address to its plans. The Milky Way will continue its long future meeting with Andromeda Galaxy, without needing your supervision. You may safely delegate all of that. Sometimes rest begins with remembering what is not your responsibility. You do not need to stabilize the stars. You do not need to manage gravity. You do not need to accelerate particles or regulate galaxy formation. For the next little while, perhaps you only need to breathe slowly and let the body remember it knows how to soften. If your eyes are heavy, that is welcome. If your thoughts are still moving, that is welcome too. Even galaxies take time to settle. There is no need to force quietness. Often stillness arrives the way dawn does, gradually, without needing applause. Perhaps notice the surface beneath you supporting your weight. Perhaps notice the rhythm of breathing, however it naturally comes. Perhaps notice the simple fact that in a universe filled with motion, you have found a place to pause. That is not small. That is skill. That is wisdom practiced in ordinary form. Many people search for peace, as if it must be permanent to count. But even temporary calm is real calm. A few quiet minutes matter. One rested night matters. One softened thought matters. Short things can still be true things. The universe taught us that too. Some bursts last seconds and remain important for billions of years afterward. Now the room may feel quieter than when we began. The day may feel farther away. Or perhaps nothing dramatic has changed except that you have spent time somewhere wider than routine. That is enough as well. There is no perfect outcome required here. Only gentleness. Only permission to loosen the grip on whatever can wait until morning. Above the roof, above the weather, above the city lights or countryside dark, the stars continue their ancient work. Some are beginning. Some are ending, some are stable for now, some carry worlds. Some have already vanished, though their light still travels. And here you are, another temporary brightness in the story, conscious for a little while, listening, learning, resting. That is a remarkable thing. Thank you for spending this time with me here at Science for Sleep. If this journey brought you comfort, curiosity, or simply a softer landing into the night, you're always welcome back. Until then, let the universe keep moving. You do not have to. You can be still now.